The universe may offer us barren worlds, but with science, ambition, time, and sheer willpower, we can sculpt them into paradises. The cosmos teems with planets, trillions upon trillions, but almost none are suited for human life. Even those that seem close, Mars, Venus, or distant exoplanets, lack the delicate balance of atmosphere, temperature, gravity, and resources that make Earth a cradle for life. If humanities expand beyond our homeworld, we must become not just explorers, but world builders, reshaping alien landscapes into thriving new homes. Where nature offers only dust and shadow, we shall weave light, warmth, and the endless dance of living things. Terraforming is the grand endeavor of transforming entire planets, moons, or other celestial bodies into environments where Earth life can flourish. It is the ultimate feat of engineering, requiring vast energy, patience, and technology to alter atmospheres, hydrospheres, climates, and even gravity itself. The process may take centuries or even millennia, but in theory, it allows lifeless or hostile worlds to be remade into lush, living habitats. Yet the goal is not always to replicate Earth. While planets within the Goldilocks zone, the region around a star where liquid water can exist, are prime candidates for terraforming, human expansion may favor worlds tailored to our preferences rather than strict Earth analogs. A planet's day length might be stretched to a 25-hour cycle to match human circadian rhythms, its land masses reshaped to maximize coastal beachfront, or its climate tuned for eternal spring. Some worlds may be sculpted into grand spectacles, towering waterfalls, endless ski slopes, or low-gravity resorts where visitors soar like birds. Terraforming is not just about survival, it is about shaping entire worlds to human ideals, whether for comfort, culture, or commerce. And those ideals will not always remain the same. Over time, a world's purpose may shift, transforming from one type of civilization to another. As explored in our Settled and Developed Planets series, a world may begin as an agricultural colony or farm planet, only to evolve into an industrial world or forge world. Some may become hive worlds, teeming with urban sprawl, while others may be fortress planets or even death worlds, shaped by conflict or catastrophe. Terraforming is rarely a single-step process. A planet may pass through many phases as its civilization advances or collapses. A world might be ruined and reborn thousands of times by its surviving peoples in the billions of years that planet will exist. And a key point today is that terraforming will often require maintenance, and without it some worlds may slowly return to inhospitable states. But not all planets will be worth fully terraforming, at least not right away. Many will remain only partially adapted, leading to the concept of para-terraforming, where domes, orbital shades, or hybrid ecosystems allow for settlement without reshaping an entire planet. Others may already harbor alien life, raising ethical dilemmas about whether transformation should be pursued at all. And beyond planets, massive space-based megastructures like O'Neill cylinders or Dyson swarms could offer more efficient alternatives to planetary habitation. Terraforming is as much a question of civilization as it is of science. The scale of such projects surpasses nations or corporations. It is the work of an advanced species wielding the energy of entire star systems. It demands vision, coordination, and a level of willpower as immense as the undertaking itself. A world is not remade in a day, nor by a single generation, but by the enduring ambition of a species determined to shape its own destiny. In this discussion, we will explore the science, technology, strategies, and ethical questions surrounding terraforming. We will look at a number of terraforming approaches and then discuss types of worlds and what we would use on them. Like all our Compendium episodes, after the introduction the sections are arranged alphabetically and you can't skip around or watch it straight. We try to keep repetition to a minimum, but each entry also tries to be reasonably self-contained, especially the last section where we review methods for handling planets with specific non-Earth-like conditions, low gravity, low light, long day, and so on. And some techniques will overlap or apply to several. We will also mention episodes that deep dive the topic in greater detail than time allows today. Some others we will look at in future episodes, and don't forget to like and subscribe for alerts when those and other episodes come out. It is a huge topic, even in summary, so we'll be here for a bit and a drink and a snack is advised. From planetary engineering techniques to adapting colonies for extreme environments, we will examine how humanity might one day forge new worlds among the stars. And thanks for joining us on this journey today about building our tomorrow. What is terraforming? Terraforming is the art and science of reshaping entire worlds, transforming barren or hostile landscapes into places where Earth life can thrive. It is a feat of planetary engineering that requires altering a world's atmosphere, climate, and even geology to make it suitable for human habitation, though more broadly, it means the intentional alteration of a planet to your preferred state, which might not be Earth-like. Aliens wouldn't be trying to make a planet like Earth, after all, but we still call that terraforming. But what exactly are we trying to change? There are countless things that make Earth what it is, but the most fundamental aspects of a world that terraforming seeks to modify include atmosphere. Pressure, composition, and breathability must be adjusted. Some planets lack any atmosphere at all, while others have toxic gases or crushing pressures. Temperature. The surface must be warmed or cooled to fall within a livable range. This often involves manipulating greenhouse gases, orbital positioning, or solar input. Water availability. Planets may need water imported, released from underground reservoirs, or redistributed to form oceans, lakes, and rivers. Gravity and magnetosphere. While gravity itself is difficult to alter, the lack of strong magnetic field may expose a planet to solar winds, gradually stripping away its atmosphere. Solutions such as artificial magnetospheres may be required. Day and night cycle. The length of a planet's day, whether it is tidally locked or has extreme seasonal shifts, can have major consequences for life. Some worlds may need artificial solutions, such as orbital mirrors, to regulate lighting. Yet terraforming is not always about replicating Earth. The goal may not be to create an Earth clone, but rather a world optimized for human needs, or even for specific industries, cultural preferences, or aesthetic choices. Some worlds might be engineered with endless coastlines, artificial mountain ranges, or low-gravity sports arenas, making them not just habitable, but uniquely desirable places to live. Some may be intentionally built harsh, prison planets or worlds for explorers and hunters. We also must recognize that terraforming is rarely a permanent transformation. A world must be maintained. Without constant upkeep, a terraformed planet could slowly revert to its original, hostile state. This may be due to atmospheric loss, climate drift, or natural geological activity undoing centuries of careful engineering. Ultimately, terraforming is not just about survival. It is the first step in creating entire new worlds, where humanity will not merely endure, but thrive. Terraforming versus para-terraforming. When people imagine terraforming, they often think of grand transformations, vast deserts turned into lush forests, thick atmospheres made breathable, and entire oceans summoned from ice or cometary impacts. Yet full planetary terraforming is a slow, resource-intensive process that can take centuries or even millennia. In contrast, para-terraforming offers a faster, more localized approach, adapting human habitats to a world rather than adapting the world to human needs. At its core, terraforming is about making an entire planet Earth-like, altering its atmosphere, climate, and hydrosphere so that life can exist freely under an open sky. It is the ultimate feat of planetary engineering, but often aided or improved by megastructures, requiring advanced technology and maintenance. Instead of pushing a planet into a new orbit to alter its sunlight levels, it may be far more practical to deploy artificial magnetospheres or solar mirrors to regulate climate and radiation. These more artificial approaches, such as gigantic magnetic fields, orbital mirrors, and vast domed habitats, fall under para-terraforming. They are often the first step in planetary transformation, allowing early settlers to establish livable environments on a dead world long before oceans and skies can be introduced. By design, Para-terraforming takes a more practical, incremental approach than full terraforming. Instead of modifying an entire planet, colonists would alter only specific regions, constructing domes, pressurized habitats, or controlled biospheres. This could range from sealed cities on airless moons to walled houses, where massive transparent canopies cover entire valleys or continents, trapping heat and oxygen while shielding inhabitants from cosmic radiation. While full-scale terraforming offers the dream of walking unprotected under an alien sun, para-terraforming provides a more immediate and flexible solution. It allows colonization of worlds that may never be fully terraformed, such as moons with insufficient gravity to hold an atmosphere, or planets with highly toxic environments. It also serves as a testing ground for eventual terraforming efforts, letting settlers establish a presence before committing to a centuries-long planetary engineering project. Yet the distinction between the two is not always clear-cut. Many terraforming efforts will likely begin with para-terraforming, gradually expanding domes in controlled environments until the surrounding world is reshaped into something more Earth-like. Conversely, some worlds may only ever receive limited terraforming, perhaps modifying an atmosphere just enough to support outdoor life, while still requiring breathing mass or minor life support. Likewise, permanent orbital mirrors and shades may be used to regulate sunlight instead of altering a planet's atmosphere. In the end, terraforming and para-terraforming are not opposing strategies, but complementary tools, and not the only options available. Some approaches may blend elements of both, while others may represent entirely distinct methods of planetary adaptation. The right choice would depend on the resources, time frame, and long-term goals of those seeking to forge new worlds among the stars. Planets versus megastructures. For all of human history, we have lived on this planet, so we tend to assume we will go out and settle other planets. Yet as we move into space, we must ask a fundamental question. Is terraforming planets the best way to expand, or should we instead build our own worlds from scratch? Terraforming is an immense undertaking, requiring vast amounts of energy and time to modify an existing celestial body. It is limited by the planet's natural conditions, gravity, orbit, composition, and location in the solar system. Some worlds may be ideal candidates, needing only minor atmospheric changes, while others may be so hostile that reshaping them is impractical. Even with advanced technology, a planet's gravity and rotational cycle cannot be easily adjusted without extreme interventions. By contrast, megastructures offer complete control. Instead of struggling to reshape an imperfect planet, civilizations could construct entirely artificial habitats, custom-built to their needs. We've spent a lot of time discussing these mighty megastructures, from Oneo cylinders, vast spinning space stations that simulate Earth-like gravity, to shell worlds, artificial planetary crusts supported by active structures. They offer many advantages, including using far less mass, or less valuable mass, than a planet would. The appeal of megastructures lies in their efficiency and adaptability. A rotating habitat can provide Earth-like gravity without requiring a planet's mass. Space stations or world-sized orbital habitats can be positioned wherever conditions are ideal, near a sun for power, in deep space for privacy, or in asteroid fields for easy resource extraction. They are modular, scalable, and not bound by planetary limitations. Yet planets remain attractive for several reasons, and we took a deep dive into the pros and cons in our episode on planets versus megastructures, a companion episode to our Megastructure Compendium. In the end, I think we'll see a lot of both, just as we'll see extensive use of both terraforming and para-terraforming, which takes us to yet another option. Terraforming versus bioforming. Terraforming is the process of reshaping a planet's environment to support human life, adjusting atmosphere, temperature, and hydrology to create Earth-like conditions. But there is another approach, bioforming, where instead of changing a world to suit us, we change ourselves, or other life forms, to thrive in alien conditions. At first glance, terraforming seems like the obvious choice. A breathable atmosphere, liquid water, and a familiar climate allow for comfortable human settlement, agriculture, and the development of civilizations much like those on Earth, and one tuned to support existing ecologies. But terraforming is a slow, resource-intensive process, requiring vast amounts of energy, technology, and time, often centuries or even millennia. Bioforming, by contrast, is a much faster and more adaptable strategy, leveraging biotechnology, genetic engineering, and cybernetic augmentation to make life itself more flexible. Instead of transforming an entire planet, bioforming allows humans, animals, and plants to be modified to survive in harsher environments. This could mean simple genetic tweaks, such as engineering crops to withstand higher radiation, lower gravity, or extreme temperatures, or more radical adaptations, such as humans who breathe different gases, tolerate intense cold, or even photosynthesize for energy. A more extreme version might involve entirely post-biological life, where consciousness is transferred into synthetic or cybernetic bodies, negating the need for any planetary changes at all. And speaking of cybernetics, this can go beyond bioforming to entirely non-biological approaches, like turning a planet into a vast computer bank full of virtual minds and AI. That's beyond our scope today, as we're focused on more classic terraforming and biology, but it's entirely possible that our future isn't on terraformed planets or vast space habitats, but on robotic worlds or inside virtual realms. Bioforming also has its own challenges. The human body is extraordinarily complex, and altering it to survive alien worlds might involve unintended consequences. But doing this to humans alone isn't enough, unless you're simply adapting a select group of colonists to an alien world that already has life. In most cases, you need to tweak our entire ecosystem and every organism in it to function in this new environment, not just individually, but in relation to each other, as predator-prey cycles will be heavily disrupted by shifts in things like gravity. A rabbit that now flees more easily in low gravity, or a predator that jumps much higher, could fundamentally change an entire biosphere. And the changes to humans are profound all on their own. While selective adaptations, such as oxygen-rich blood for high-altitude survival, might be relatively simple, deeper changes could lead to unpredictable medical or psychological effects. Socially, it raises questions about identity. Would heavily modified humans still be considered human? Would civilizations diverge into entirely different species based on the worlds they inhabit? The inevitable hybrid approach. Terraforming and bioforming are often framed as competing strategies, one reshaping the planet to fit life, the other reshaping life to fit the planet. But in practice, the future of planetary adaptation will almost certainly be a fusion of both. A truly effective approach will combine planetary engineering with biological adaptation, creating a hybrid system where both worlds, natural and engineered, meet in the middle. The reality is that we would expect any planet to be surrounded by orbital habitats and megastructures. Some focused on human settlements or nature preserves, others devoted to computation. Some of them, the para-terraforming devices, helping keep the world livable, while a population below uses a mix of all these options. A finished world may not simply have Earth-like soil covering alien strata, but another layer of infrastructure and computation lying between them, buried from sight beneath lush gardens. And perhaps many hybrid regions or layers might exist too. Even on Earth, life adapts to its surroundings. Humans have already modified crops to withstand droughts, bred livestock for specific climates, and developed medicine to survive in harsh environments. A civilization expanding beyond Earth will continue this trend, using bioengineering to make plants and animals more resilient while simultaneously engaging in large-scale planetary modifications. Terraforming alone may not be fast enough or practical for every world, and bioforming alone may not provide enough of a stable, self-sustaining ecosystem. The two will work in tandem. For example, a partially terraformed planet with a thin but oxygen-rich atmosphere may still require humans to wear breathing masks, but through bioforming, colonists could develop enhanced lung capacity or even genetic modifications allowing them to tolerate lower oxygen levels. Crops might be engineered to thrive in alien soil, while atmospheric processors and greenhouse domes gradually expand, stabilizing the environment over generations. This hybrid approach also acknowledges the realities of planetary diversity. Some planets may be well suited for full-scale terraforming, but others, such as low-gravity moons, rogue planets, or Venus-like infernos, might only ever support human life if significant biological or technological adaptations occur. A civilization with the ability to both modify planets and modify itself has a greater range of options than one limited to just one strategy. Whether or not they choose to employ a given strategy is up to them, but they do have it available. In many ways, this mirrors how we already approach our own planet. we do not terraform Earth, but we shape it. Cities have artificial microclimates, underground facilities, and climate-controlled environments. We modify crops and livestock for local conditions. And in extreme places like deep-sea research stations or Antarctic bases, our survival depends on both environmental engineering and biological adaptation. As humanity expands into space, this balance will only grow more pronounced. Some worlds may receive gradual terraforming over centuries, while in the meantime, settlers will use genetic engineering, cybernetics, and controlled habitats to bridge the gap. The longer a civilization exists beyond Earth, the more it will blend these approaches, not just shaping plants to suit us, but shaping ourselves to fit the vast, varied, and often inhospitable universe. The line between terraforming and bioforming is not a hard boundary, it is a spectrum, and the future of humanity will likely be written across it. It is also like a moving goalpost, as the abilities and desires of the people living there may shift with time. Ethics and debate, preservation versus transformation. Terraforming offers humanity the chance to reshape entire worlds, but should we? The ethics of planetary transformation raise profound questions about preservation, responsibility, and unintended consequences. One major concern is whether we have the right to alter alien worlds, especially if they already harbor life. Even microbial ecosystems could represent unique, independent biospheres, and modifying them could be seen as an act of destruction rather than creation. Would humanity be caretakers, stewards, or invaders? If intelligent life exists elsewhere, would we consider it ethical for them to terraform Earth to suit their needs? Even lifeless planets pose ethical dilemmas. Should we preserve them as untouched natural wonders? Should we terraform only those that seem beyond use otherwise? Some argue that barren worlds are blank slates, waiting for life to take root, while others see them as cosmic artifacts that deserve protection. There's also the question of long-term impact. Terraforming is a commitment, not just to shaping a planet, but to maintaining it. What if a project fails midway, leaving behind a half-transformed, unstable world? What if a terraformed planet is later abandoned? Should it be left to decay, or would we have an obligation to keep it habitable? These are complex questions without easy answers. For a deeper dive into the ethical considerations of terraforming, check out our episode, Is Terraforming Plants Ethical? But as we move forward, we must weigh the costs, the consequences, and the responsibilities that come with reshaping entire worlds. Terraforming as a civilization-scale endeavor. Terraforming is not the work of a single generation or nation. It is a vast civilization-spanning endeavor. Reshaping a planet takes centuries, requiring immense energy, infrastructure, and coordination on a planetary or even interstellar scale. No single human could undertake such a project alone. The sheer energy demands, melting ice caps, thickening atmospheres, or redirecting asteroids, requires a civilization capable of harnessing power on a Kardashev Type 1 or even Type 2 scale. Terraforming also demands long-term economic and political stability, as a half-terraformed world is not habitable but a work in progress, requiring constant upkeep. Even with advanced automation, terraforming remains a massive challenge, requiring not just ambition, but the right tools and technologies. In the next section, we will explore the key methods by which entire planets might one day be transformed. Terraforming technologies and techniques. Terraforming is not a single process, but a vast collection of engineering solutions, environmental modifications, and biological adaptations. Depending on the nature of the world being transformed, different techniques may be required, from thickening an atmosphere to shielding its radiation, or even stabilizing an entire planet's orbit. Some of these methods are based on established science, such as atmospheric manipulation or hydrospheric engineering, while others, like artificial gravity or planetary scale nanotechnology, remain speculative. In practice, most terraforming projects will rely on a combination of multiple techniques, often in conjunction with para-terraforming or bioforming strategies. In this next section, we will explore the key methods that could allow humanity to reshape alien worlds, one technology at a time. Artificial gravity solutions. Gravity is one of the most difficult planetary characteristics to alter, yet it plays a crucial role in human health and long-term habitability. Low gravity can lead to muscle atrophy, bone loss, and various physiological issues, while extreme gravity makes construction, transportation, and even human movement far more challenging. Bioforming may be an option, but there are also terraforming techniques available. For asteroids and small moons with microgravity, one approach is centrifugal habitats, rotating space stations or large dome cities with spinning sections embedded into the surface, simulating gravity via centrifugal force. A related concept is the bullhab, which we discussed in the Domes of Mars. This design combines local gravity with spin gravity, orienting forces downward and outward along the floor of the bowl, at a changing diagonal, rather than horizontal or vertical alone. Another method is simply adding mass by importing material, such as asteroids or comets, to increase a planet's gravitational pull. However, this requires an immense amount of mass and is rarely practical. It also consumes vast quantities of valuable matter, whereas hydrogen, helium, and dark matter make up the overwhelming majority of the universe's mass and could be used more efficiently. By incorporating these into planetary shells, we could construct shell worlds without depleting rarer elements, thus allowing us to construct hundreds if not thousands of times as many planets as the natural method. An alternative approach involves placing artificial black holes, potentially created from those abundant elements, inside planets or moons to generate gravity. We explore this concept in depth in Moon Megacities. Surprisingly, there is little risk of such a black hole consuming the planet. Since they are incredibly small, only minimal amounts of matter can enter them. Furthermore, as material falls in, it becomes superheated and forms a dense plasma barrier, effectively clogging the entryway. Ironically, this process would make the planet's core behave much like the natural molten cores of terrestrial planets, maintaining heat and convection in a similar manner. More speculative solutions include gravitic engineering, where exotic matter, space-time manipulation, or controlled gravitational fields could artificially alter local gravity levels. While far beyond current technology, it remains a possibility for ultra-advanced civilizations. For more on this, see our Gravity Tech episode or the Clark Tech Compendium. For planets with excessive gravity, structural adaptation is often the more viable solution. Buildings, vehicles, and even human biology could be engineered for high-gravity environments, with exoskeletons or genetic modifications helping inhabitants function. Another approach is planetary mass redistribution, stripping material from a high-gravity world to construct multiple smaller planets or thousands of Earth-sized shell worlds filled with hydrogen and helium from a gas giant. We discussed further methods in high-gravity planets, including spinning ring habitats around the equator, which would reduce gravity for those on the surface. Atmospheric manipulation. A planet's atmosphere is one of the most crucial factors in making it habitable. The right composition, pressure, and density regulate temperature, block harmful radiation, and provide the oxygen needed for life. Yet most worlds have atmospheres that are too thin, too thick, toxic, or entirely absent. Terraforming plans often begin with atmospheric manipulation, altering the gases that surround a planet to create a more hospitable environment. Thickening or creating an atmosphere. Many candidates for terraforming, such as Mars or the Moon, lack a significant atmosphere. To create one, gases must be imported or released from local resources. This can be achieved by polar or subsurface ice melting, releasing trapped carbon dioxide and water vapor through artificial warming. This can be done in many ways, like solar mirrors or even nuking the caps, which we examined in the episode Nuking Mars. Volcanic activation, using nuclear detonations or geothermal engineering to release underground gases. Comet impacts, delivering water, ammonia, and other volatiles from icy bodies. Direct gas release, transporting nitrogen and oxygen from gas giants or synthesizing them chemically. Even with these methods, atmospheric retention remains an issue, especially on low-gravity worlds where gas slowly escapes to space. Solutions such as artificial magnetospheres to reduce solar wind stripping or continuous replenishment may be necessary. Thinning or removing an atmosphere. Other planets such as Venus suffer from the opposite problem, an atmosphere that is too thick, trapping heat and creating a runaway greenhouse effect. Strategies to reduce atmospheric density include solar shades and orbital mirrors, cooling the planet to cause atmospheric gases to condense and settle, chemical sequestration, binding excess carbon dioxide into carbonates or synthetic materials, atmospheric stripping, using mass drivers or gigantic vacuum towers to eject gas into space, hydrogenation, injecting hydrogen to react with CO2 and produce water and graphite, reducing the greenhouse effect, adjusting composition. A breathable atmosphere requires a specific balance of gases. Too much oxygen leads to dangerous wildfires, too much carbon dioxide creates suffocating conditions, and toxic gases like methane or sulfur dioxide must be eliminated. Techniques for adjusting composition include photosynthetic bioforming, introducing engineered microbes to convert CO2 into oxygen over time, industrial-scale gas processing, deploying atmospheric scrubbers and filtration plants to remove or convert unwanted gases, electrostatic separation, using electromagnetic fields to selectively strip lighter gases from the atmosphere. Indeed, we can use a similar method to harvest matter off of stars by star lifting. In many cases, planetary engineering will involve a mix of these techniques. A partially terraformed world might have an atmosphere that supports life, but requires breathing mass, while others may rely on artificial support indefinitely. See our various episodes on Venus and Mars terraforming for specific challenges in atmospheric engineering. Bioforming and genetic engineering. As we discussed earlier, while terraforming seeks to alter planets to fit life, bioforming takes the opposite approach, modifying life to survive in alien environments. But it also can be used not just as an alternative to terraforming, but also as a means of terraforming. Microbial pioneers and engineered ecosystems. The first step in bioforming a world often involves microbes. Engineered bacteria, algae, and lichens can be introduced to generate oxygen, break down toxic compounds, or create soil for future plant life. Some may be designed to endure high radiation, extreme cold, or acidic conditions, gradually laying the foundations for larger ecosystems. Oxygen-producing microbes. Similar to cyanobacteria on Earth, they could convert CO2 into breathable oxygen. Radiation-resistant bacteria. Engineered extremophiles could minimize DNA damage in organisms exposed to harsh cosmic rays. Soil conditioning fungi. Break down regolith into nutrient-rich soil, enabling plant life to take root. Genetically modified flora and fauna. Once a basic biosphere is established, larger organisms can be adapted to new environments, and may be gradually replaced or adapted as the world moves to more terrestrial conditions, much as life adapted to the sweeping changes Earth is believed to have undergone over the eons. This might include heat-resistant or cold-tolerant crops, allowing agriculture on planets with extreme temperatures, low-light plants, engineered to photosynthesize in dim conditions useful for distant exoplanets or underground farms, animals with modified metabolisms, capable of surviving lower oxygen levels or altered food chains. Adapting humans. For plants that remain only partially terraformed, bioforming could extend to the colonists themselves. Modifications might include enhanced lung capacity or synthetic oxygen carriers, allowing survival in thinner atmospheres, radiation resistance, increased melanin production, or DNA repair mechanisms to mitigate exposure, microgravity adaptations, bone density enhancements, or muscular reinforcements for low-gravity environments. Some extreme bioforming proposals involve integrating cybernetics, converting human minds into digital consciousness, or even engineering post-human species designed to thrive in specific planetary conditions. And this could be anything from wings to gills and beyond. Comet and asteroid bombardment. One of the most dramatic methods of terraforming involves harnessing the raw power of comet and asteroid impacts to reshape a planet's surface, atmosphere, and water supply. While often depicted as catastrophic events, controlled bombardment offers an effective way to introduce essential materials, especially water and volatiles, to dry or barren worlds. However, this is a process measured in centuries or even millennia, and the effects on a planet's appearance and structure are profound. Terraforming is inherently destructive to a planet's original landscape. As I like to say, you aren't just spray painting the place blue and green. Mountain ranges will slide down, continental plates, if it has any, will creak and shift. Water delivery and atmosphere building. Many planets and moons lack significant water, and without it, large-scale terraforming is impossible. Comets, rich in water ice and frozen gases, provide an abundant source. By redirecting icy comets, such as Halley's Comet, which contains about 300 billion tons of water ice, a planet could gradually accumulate vast oceans. However, the sheer scale of the effort is staggering, and if comets were fragmented right before hitting and allowed to melt in the sky, it would amount to a torrential downpour of boiling hot rain planet-wide for thousands of years in order to get deep oceans like Earth has. To match Earth's oceans, millions of comet-sized bodies would need to be redirected. Even supplying a modest and shallow ocean would take tens of thousands of major impacts. The process could take millennia unless highly efficient methods are used. Asteroids, while less useful for water delivery, offer valuable metals and silicates that could help build an atmosphere by releasing trapped gases upon impact. Carbon-rich asteroids, for instance, might contribute to carbon dioxide levels, jump-starting a greenhouse effect on colder worlds. You might intentionally drop them on frozen polar ice caps too. Asteroids might be towed in to help build the orbital infrastructure of habitats, power collectors, and terraforming megastructures, and have some of their resources pooled for use on the planet below too. One thing to keep in mind is that no planet is ever short of oxygen. Most rock is composed of a large fraction of it, so it is other volatiles the planet needs, and you may bring hydrogen in to combine with oxygen locally sourced to make water, as a water molecule is 89% oxygen by mass, and stars and gas giants can both be harvested for hydrogen. Altering planetary appearance. Planetary bombardment fundamentally reshapes a world's surface. Each impact releases massive energy, creating craters, volcanic activity, and atmospheric disturbances. Cratered landscapes. The planet could look like a war zone for thousands of years before erosion smooths it out, though it might also make for beautiful crater lakes and landscapes with a little biology and effort. Global temperature shifts. Repeated impacts cause extreme heating, potentially creating brief runaway greenhouse periods. New mountain ranges and rift valleys. Some impacts could drive up entire mountain chains or carve out vast basins. This might be intentional, and inciting volcanic activity is a good way to release gases for an atmosphere, albeit not necessarily a breathable one by terrestrial organisms, though it might be perfect for some tailored organisms intended for early terraforming purposes. Over long enough timescales, these transformations settle into a more stable planetary system. The heavy bombardment period of Earth's early history, for instance, helped bring our oceans and atmosphere into being, but also left behind scars like the Moon's craters, which remain unchanged for billions of years. It emphasizes an important point about terraforming. It utterly changes a world more than a massive nuclear war would. Imagine an entire mountain range that's never seen rain before mudsliding over half a continent. Again, you're not just spray painting a planet green and blue. The challenges of impact engineering. While this method offers an effective way to deliver water and volatiles, the risks are immense. A poorly aimed comet or asteroid could devastate a planned colony, and too many impacts in a short period could trigger uncontrolled climate shifts. Additionally, each strike releases immense heat, possibly vaporizing water before it can settle. As we spread out into the galaxy to planets that may take us hundreds of thousands of years to send colonists to, we might send automated probes in advance to bombard lifeless worlds so that when our settlers did arrive, the planet's landscape had settled back down. Needless to say, such automated systems, designed for pushing asteroids and comets into collision orbits, need to have major safeguards in place for avoiding bombing worlds with existing life on them. Controlled bombardment would require precision engineering, using gravity assists, fusion-powered tug ships, or mass drivers to adjust trajectories over decades. It's a long game, but for worlds that lack vital resources, it may be the only way to make them habitable. We looked at this more in our episode on comet mining. While slower and messier than other terraforming techniques, comet and asteroid bombardment remains one of the most straightforward ways to fundamentally reshape a planet. Given enough time and patience, it could transform even the driest, most desolate world into an ocean-bearing paradise. Domes and world houses. For worlds that cannot be fully terraformed, either due to extreme conditions, lack of resources, or simple practicality, domes and wardhouses offer a fast and scalable alternative. These structures allow for controlled Earth-like environments on otherwise hostile planets without needing to alter an entire world. Domes, small-scale habitats. Domes are the simplest form of para-terraforming, enclosing cities, farms, or industrial zones within pressurized, climate-controlled bubbles. They allow for rapid colonization of airless worlds, high-radiation environments, or planets with toxic atmospheres. Domes can be made of transparent composites, reinforced alloys, or even aerogel-supported membranes, providing insulation and protection from cosmic rays. Domes also have floors, as the local regolith isn't likely to be healthy to have around, and is a reminder that they might be made to float on a sea, or under a sea, or even the clouds on places like Venus. While traditionally envisioned as isolated city-sized structures, domes can also be linked into vast interconnected networks, creating a web of habitable zones across the planet's surface. They can even be partially buried for extra protection, similar to lunar lava tubes. However, they require maintenance and are vulnerable to structural failures, unlike full terraforming, which offers long-term habitability. World houses, terraforming in a bubble. A step beyond domes, world houses take the same principle and apply it on a continental or even planetary scale. Instead of enclosing a city, an entire valley, region, or hemisphere is covered by an immense transparent canopy, trapping heat, oxygen, and moisture, or a partially mirrored surface to keep light out on hotter planets. We deep dive these in their own recent episode, but to summarize, world houses provide a middle ground between domes and full terraforming. They allow breathable atmospheres without needing to alter an entire planet. They retain heat and water, making frozen or dry worlds more hospitable. They shield against radiation and meteorites, reducing colonist exposure. They work on worlds with weak gravity, keeping an atmosphere in place artificially. They are particularly well suited for planets with thin or unstable surfaces, such as Mars or Titan, where a full-scale atmosphere transformation might take millennia. On Titan, for instance, you already have an atmosphere thicker than Earth's, and here you need the dome to keep it out, as it's not even a little bit breathable. While more ambitious than domes, they still avoid the immense energy requirements of complete terraforming. The future of enclosed worlds. Both domes and world houses represent near-term solutions for early colonization, as well as long-term alternatives for worlds that can never be fully terraformed, as their gravity just doesn't permit air retention, even in cases like asteroids with black holes in them that have normal Earth gravity on the surface. They also allow for precise environmental control, letting humanity sculpt not just livable spaces, but ideal ones, with custom climates, ecosystems, and even artificial day-night cycles. As such, they might be normal features even on Earth-like planets where they offer an extra layer of advantage over simple open sky. We may eventually see them in our own desert and tundra environments here on Earth. In the end, whether through domes sheltering the first pioneers or world houses covering entire planets, these enclosed habitats offer a bridge between planetary engineering and more immediate practical colonization. Geoengineering and climate control. Terraforming a planet requires more than just adjusting its atmosphere. It also means managing its climate and geophysical systems to ensure long-term habitability. Geoengineering and climate control techniques allow civilizations to fine-tune planetary weather patterns, temperatures, and even geological activity to create stable, livable conditions. Altering temperature and greenhouse effects. One of the most fundamental challenges in terraforming is managing planetary temperature. A planet that is too cold, like Mars, requires warming, while a world like Venus needs cooling. There are multiple ways to achieve this. Increasing greenhouse gases for cold planets by releasing carbon dioxide, methane, or supergreenhouse gases like perfluorocarbons, PFCs, to trap heat. Reducing greenhouse effects for hot planets by removing atmospheric carbon dioxide, injecting reflective aerosols, or using chemical reactions to lock greenhouse gases into solid form. Solar mirrors or shades placed in orbit to regulate sunlight exposure, either by amplifying or blocking incoming radiation. Altering planetary albedo by changing surface reflectivity, adding dark materials to absorb heat or reflective materials to scatter it, This could be as simple as seeding the ice caps with black dust to encourage melting, or covering deserts with reflective films. Controlling weather and water cycles. Once a planet reaches a viable temperature range, managing its climate remains an ongoing challenge. Some key techniques include seeding clouds or rainstorms by introducing aerosols or particles into the upper atmosphere to promote precipitation. Controlling wind patterns through massive topographical adjustments, such as redirecting jet streams by constructing artificial mountains, ridges, or heat islands. Regulating ocean currents by constructing artificial reefs, underwater barriers, or even adjusting the salinity of oceans to steer warm and cold currents. These methods could prevent extreme droughts or floods, stabilize seasonal weather, and maintain a more Earth-like hydrological cycle. Geological adjustments. Climate is also influenced by a planet's internal heat and geological activity. Volcanic activity plays a role in atmospheric composition and long-term climate regulation, so controlling it would be crucial. Triggering or suppressing volcanic eruptions to release or contain gases. This might involve drilling pressure release vents into planetary crusts or artificially inducing minor eruptions in a controlled manner. Strengthening or weakening tectonic activity by altering planetary mass distribution, such as moving vast amounts of material through asteroid impacts or artificial excavation. Artificial geothermal regulation, where underground heat vents could be used to control localized warming or cooling effects. The long-term challenge of climate control. Geoengineering is not just a one-time terraforming tool, but an ongoing necessity for planetary maintenance. Even Earth requires constant climate management to prevent environmental degradation. Even ignoring human actions, its climate is not stable and never has been, and this would only be more the case on planets we are pushing to Earth-like conditions and have to work constantly to keep that way. Terraforming a world means taking responsibility for its long-term climate stability, ensuring that shifts in atmospheric composition, ocean currents, or geological forces do not gradually undo centuries of work. Hydrospheric Engineering. Water is essential for life as we know it, but not all planets have the right amount or the right distribution of water to support a thriving biosphere. Some worlds may be arid wastelands, while others are probably covered in endless oceans with little to no dry land. Hydrospheric engineering is the science of controlling and distributing water on planetary scales, ensuring that an environment is not just habitable, but also sustainable. For dry worlds, water can be imported by redirecting comets, ice-rich asteroids, or even siphoning from the icy moons of gas giants. However, as we discussed in our section on comet and asteroid bombardment, this process is slow, requiring millennia to build oceans if done at a safe rate. Melting existing ice deposits, whether at the poles or in subterranean reservoirs, is often a more immediate solution, utilizing greenhouse gases, solar mirrors, or geothermal tapping to release stored water. Conversely, ocean worlds may require land reclamation efforts. Floating cities, artificial islands, and submerged domes could be employed, while large-scale evaporation or ice formation could be induced to redistribute excess water. If planetary engineering permits, lowering ocean levels by shifting water into underground reservoirs or polar ice caps may also be an option. Indeed, you could keep a planet warm while freezing water in its poles by shading just those polar regions and pumping water into it to freeze on top vast tall continents of ice, which would be pushed ever outward into those warming areas by gravity, which might result in some fairly interesting ecologies akin to those we would expect on the twilight bands of tidally locked worlds. Water distribution is also a challenge. Even if a planet has abundant water, it may be locked in glaciers, spread too thin, or situated in the wrong places. Terraforming efforts may involve constructing vast artificial rivers, canals, or reservoirs, ensuring that water cycles function efficiently across the planet's surface. Likewise, planetary topography could be adjusted through controlled tectonic activity or mega-engineering projects to create ideal drainage basins and climates, or even continent-sized rafts. You could even engage in seawalls and active pumping to create oceans at different sea levels, which might make for some truly epic waterfalls, miles wide or tall. Hydrospheric engineering is not just about water supply. It also involves managing planetary weather patterns, ocean currents, and hydrological cycles to sustain an ecosystem long term. Without careful planning, even a well-watered world could suffer from runaway flooding, salt buildup, or severe drought cycles. A stable and controlled hydrosphere is essential for any terraformed world to remain livable over geological timescales. Magnetosphere Generation. A planet's magnetosphere serves as a vital shield, protecting its atmosphere and surface from solar and cosmic radiation. Without a strong magnetic field, our world's atmosphere is gradually stripped away by the relentless bombardment of solar wind, as seen with Mars, which lost most of its early atmosphere over billions of years. Additionally, a lack of magnetic protection exposes any surface life to dangerous radiation, making long-term habitation difficult. Thus, for many terraforming efforts, restoring or artificially generating a magnetosphere is essential. One proposed method is to restart a planet's core dynamo by heating and agitating its interior. This could be done by introducing artificial black holes, similar to what we discussed in our Moon Megacities episode, or by using geothermal tapping, tidal flexing, or even nuclear devices to induce convection in the core. However, this is an extremely slow and energy-intensive process with no guarantees of success, and would likely render that planet unusable while it was going on, given the sheer scale of energy and forces involved in blowing up a planetary core. A more practical approach is to generate an artificial magnetosphere using large-scale electromagnetic devices. One of the leading proposals, which we explored in depth in our episode Giving Mars a Magnetosphere, suggests placing a powerful magnetic field generator at the L1 Lagrange point, where the Sun's gravity and Mars' gravity balance out, to create a spot that orbits at the same rate as Mars does. Note that every two-body system has a L1 Lagrange point between them, as well as 4 other points, and this is not where gravity is 0, merely reduced from what it would be to allow a slower than normal orbital rate, matching in this case that planet's orbital rate. See our Lagrange point settlement episode for further explanation, but this lets us stick something between the Sun and planet that stays there even as the planet moves. This could be a sunshade for lowering sunlight hitting that planet, or in this case a device for deflecting solar wind. This device would create a protective magnetic bubble around the planet, shielding it from solar wind in much the same way Earth's own magnetosphere does, and powered by that same solar radiation. Surprisingly, while the energy budget is quite large for such a project, it is way below the solar budget of a planet and might even be viable with modern power production scales. For more local efforts or for shooting against sources besides your Sun or in binary systems, orbital or surface-based superconducting loops could generate localized magnetic fields, protecting settlements or entire regions rather than the whole planet. These could be constructed as planetary rings or embedded into key locations, such as poles or high radiation zones. Additionally, some worlds may not need a magnetosphere if other countermeasures are in place. Thick atmospheres, dense cloud cover, or subsurface habitats can also provide protection from radiation. In such cases, a planetary shield may be unnecessary, especially if the world is already in a low-radiation environment such as a rogue planet or a moon with a thick ice shell. Ultimately, magnetosphere generation is a crucial step in stabilizing any terraformed world, particularly those close to their stars or lacking natural magnetic protection. Whether through planetary-scale engineering or targeted shielding, ensuring a world's long-term atmospheric and radiation stability is key to making it truly habitable. Today we are exploring how to settle and terraform strange new worlds, but first we have to get there, and that means surviving a long journey through dangerous interstellar space. To swim through deep space, it might help if your ship is mostly made of water, an option we explore in our latest exclusive, Fishbowl Starships. This episode explores how future starships might use water as more than life support, turning into layered shielding that guards against radiation, heat, and even micrometeoroids. It's a concept that complements terraforming perfectly, crafting vessels that carry pieces of Earth's biosphere into the void, wrapped in oceans and ecosystems. And it's just one of many ideas we explore in our monthly exclusive Nebula content. You'll find Fishbowl Starships and dozens of other exclusive episodes there, along with every SFIA episode that debuts on Nebula early and ad-free. Enjoy extra content from myself and other great creators, all while supporting the show directly. And it's not just non-fiction content. Join Nebula and enjoy exclusive content like The Sojourn, a Nebula sci-fi audio drama, where survival depends as much on trust as it does on technology. Set in a distant and dangerous star cluster, it's perfect for fans of space battles and the human stories behind them. Just head to go.nebula.tv/IsaacArthur to sign up for $3 a month with the annual plan, and help us bring more science fiction concepts closer to science fact. Mass and orbital adjustments. Altering a planet's mass or orbital characteristics is among the most extreme and energy-intensive forms of terraforming. While adjusting surface conditions like temperature, atmosphere, or hydrology is difficult, changing a planet's fundamental position or size requires truly astronomical levels of energy. However, there are cases where such adjustments might be necessary or even preferable to other forms of terraforming. Orbital adjustments. A planet's orbit dictates its temperature, seasonal cycles, and overall climate stability. Moving a world closer to or farther from its sun could bring it into the habitable zone, or Goldilocks zone, where liquid surface water can exist. This might be necessary for planets that are too cold due to being too far from their star, such as Mars, or too hot like Venus. It is important to understand the sheer scale of energy involved though. The orbital energy of Earth around the Sun is approximately 2.65 times 10 to the 33rd joules. In comparison, this is about 5 trillion times the current annual energy consumption of human civilization. But the other side of that is that such huge energies are only a few months of the Sun's power output, so it is viable for Kardashev-scale civilizations, who might have huge power beaming arrays built by vanguard settlers to help slow down incoming colony ships, and which might also be used for such planetary shifting efforts. Another method for orbital adjustment is gravitational interactions with asteroids, moons, or other planets, using repeated close flybys or capturing large masses to gradually shift a planet's trajectory over millennia. Another more direct but highly challenging approach would be attaching massive solar sails or asteroid-based reaction mass drivers to slowly push a planet into a new orbit using sunlight pressure or momentum exchange. Theoretically, a planet could also be shifted by a series of controlled asteroid impacts, though this would require careful coordination to avoid catastrophic consequences. These same techniques can be used, and an order of magnitude more easily, to alter planetary spin rates and day length, and thus may be more common. Mass adjustments and planetary harvesting. Mass affects both a planet's gravity and its ability to hoard an atmosphere. If a world is too small, such as Mars, it struggles to retain an atmosphere over geologic timescales. If it's too massive, like a super-Earth, its gravity might be too intense for comfortable human habitation. While altering a planet's mass is impractical with current technology, possible methods include adding mass by importing asteroids, comets, or even artificial black holes to increase gravity and atmospheric retention. We might even theorize using wormholes to move mass from planet to planet. However, this requires vast amounts of material and is unlikely to be an efficient method for terraforming. Removing mass by stripping away a planet's outer layers, mining material for use elsewhere, or constructing multiple smaller planets out of a single large one. This might allow the formation of multiple habitable worlds from a single oversized super-Earth. This process ties directly into planetary harvesting, which we explored in detail in our Harvesting Planets episode. While civilizations may be hesitant to dismantle major habitable planets, smaller worlds such as Mercury, Venus, or Mars could be prime candidates for large-scale material extraction. This could involve mass driver systems, orbital elevators, or even self-replicating robotic miners stripping away planetary crusts over millions of years. Many super-Earths deemed too massive for comfortable settlement might be brought down to size and their mass added to other worlds to make them habitable. You might make shell worlds out of them too, far more numerous and filled with mass from gas giants. One super-Earth and one Jovian might let you make several hundred Earth-like shell worlds. A more radical approach would be the gradual disassembly of gas giants, extracting their hydrogen and helium to sustain fusion reactors, construct artificial planets, or extend the lifespan of a star through controlled starlifting. These methods require enormous infrastructure, but could provide resources for Dyson swarms, vast megastructures, or interstellar expansion. And shell worlds are a great place to store that extra mass for a few billion years. terraformed for habitation in the meantime. Our focus today is on altering planets, not stars, but stellar engineering is viable too, and may be part of our terraforming endeavors. Practicality and limits. Adjusting a planet's orbit or mass is among the most extreme forms of planetary engineering. While it may be necessary for some long-term terraforming efforts, most worlds will likely be modified through local environmental engineering rather than large-scale physical alterations. Even with highly advanced technology, shifting a planet's position or composition remains one of the most difficult and ambitious challenges in planetary science. However, civilizations that master planetary harvesting may gradually reshape entire solar systems, whether for resource extraction, terraforming, or long-term stellar management. Megamirrors and solar shades. Speaking of stellar management, one of the most powerful tools for planetary engineering is controlling how much sunlight a planet receives. This can be done without moving a planet further or closer to a star, or tinkering with that star's output using some of the methods discussed in the Megastructure Compendium, like star boosting or star lifting. Whether the goal is to warm a frigid world, cool a runaway greenhouse planet, or even manage seasonal shifts, mega mirrors and solar shades offer a means of fine-tuning a planet's climate with precision. These massive orbital structures can reflect, redirect, or block sunlight, providing a level of environmental control that is often far more energy efficient than attempting to modify a planet's atmosphere or geological features directly. They also need not be in orbit. You might place them at the L1 Lagrange point directly between a planet and its parent star, or in the region around them in the case of mirrors or lenses to seamlessly boost the sunlight coming in. For planets with rotation rates far too slow for viable day length, like Venus or a tidally locked planet, we can even block all natural sunlight and then use mirrors to introduce a 24-hour day to that world. This can be made to look identical to a sun, which isn't actually that tricky given that none of us ever look at the sun directly, and it is blurry even at sunset. You would never be able to tell by your own naked eye that millions of mirrors or shades, each miles across, were floating in front or near it. For planets that are too cold, such as Mars or icy exomoons, giant orbital mirrors can be used to concentrate additional sunlight onto the surface. This can even be specific to certain regions so as to just warm one area up, like your initial landing site. These mirrors, often envisioned as ultra-thin reflective films or swarms of autonomously controlled reflectors, could provide enough warmth to thaw frozen landscapes and stimulate atmospheric thickening. By positioning mirrors at the right angles, targeted regions could receive more light, potentially allowing for localized climate control over cities or agricultural zones. Conversely, for planets that are too hot, such as Venus or other greenhouse worlds, solar shades can be deployed to block or scatter incoming sunlight, cooling the planet over time. Placed at the L1 Lagrange point between the planet and its star, a thin but extensive sunshade could reduce solar energy input without needing to modify the planet's atmosphere. Over decades or centuries, this could allow for a controlled drop in temperature, possibly aiding efforts to make Venus or similar worlds more habitable. See Winter on Venus for how that process works, including the atmosphere liquefying to rain down into carbon dioxide oceans below. In some cases, these structures could even serve dual purposes. As mentioned, we could use the solar shades to fix Venus's day length down from hundreds of days to just one normal Earth day. A system of orbital mirrors and shades could regulate seasonal extremes, reducing harsh winters and scorching summers on planets with eccentric orbits. On tidally locked worlds, where one side is perpetually in daylight and the other in darkness, orbital reflectors could help balance temperature differences, creating a more stable global climate. And while you can make these look like natural suns or moons, you might enjoy giving a planet sun rings or a dozen dimmer sun mirrors. Again, terraforming can help us make planets like Earth, but it also allows us to do things which are not like Earth, or which are not like any natural planet at all. Building and maintaining these structures at a planetary scale would be an immense engineering challenge, but far easier than altering a planet's orbit or remaking its atmosphere from scratch. In the end, they only need to be as thin as tin foil, and in space, with no wind or rain, a single small metallic asteroid could provide all the material you need to create millions of square miles of long-lasting mirrors and shades, compared to traditional terraforming efforts that require vast amounts of resources and energy. Megamirrors and solar shades offer a relatively low-tech, high-impact method of planetary climate control. Oxygenation and soil processing. Oxygen is one of the most crucial elements for human life, yet most planets and moons lack a breathable atmosphere. Fortunately, oxygen is one of the most abundant elements in the universe, often locked away in rock, ice, and minerals. The challenge of terraforming isn't finding oxygen, it's extracting it in useful forms and keeping it in the atmosphere. Bake it out of the ground and you leave a lot of material ready to reabsorb it, though metal production tends to produce oxygen as a waste product, so if you're doing mass construction on a new planet, it may provide lots of oxygen for you to breathe. Most rocky planets and moons are rich in oxygen, but it is chemically bound in silicates, oxides, and other compounds. Earth's crust, for example, is nearly 50% oxygen by mass, yet our breathable air comes primarily from biological processes. To terraform a planet, oxygen must be liberated from its chemical bonds. One way to do this is through high-temperature processing, such as using extreme heat or chemical reactions to break down rocks and release oxygen. Electrolysis, which uses electricity to split oxygen from water, or minerals or ice, is another viable method, already tested on a small scale with Mars mission technology like MOXIE. You can also nuke it off or burn it out with star-powered energy beams, and while the oxygen will slowly sequester back into the material on the ground, so long as you're not letting that churn to expose more layers below, most of it won't all seep back in. Ice-rich worlds and moons provide another oxygen source. Water ice, H2O, is roughly 89% oxygen by mass, meaning that even a relatively small amount of water contains an immense amount of breathable oxygen. Melting ice and splitting water molecules via electrolysis can provide both oxygen for breathing and hydrogen for fuel. On frozen exoplanets or moons like Europa, Titan, or Triton, this method could jumpstart a breathable atmosphere while also supporting energy production. Soil processing plays a dual role in terraforming. Beyond just extracting oxygen, modifying planetary soil, often called regolith processing, is necessary to support plant life. Many extraterrestrial soils lack the right nutrients, contain toxic elements, or are too compacted to support agriculture. By introducing microbes, bioengineered bacteria, or chemical treatments, soil can be enriched to sustain plant life, which in turn helps cycle oxygen naturally into the atmosphere. Of course, as mentioned, releasing oxygen into an atmosphere is not enough. It must be retained, and it can leak into space, not just back into the ground or sea. Many planets, like Mars, lack a strong magnetosphere, meaning solar wind can gradually strip away an atmosphere. Any long-term terraforming effort must pair oxygen production with magnetosphere solutions or ongoing replenishment to counteract losses over time. Terraforming a planet's atmosphere is a slow process, but given that oxygen is already locked within rock and ice in vast quantities, the real challenge isn't scarcity, it's extraction and stability. If these obstacles can be overcome, even the most barren worlds could one day support breathable air. Planetary shells and artificial crusts. Terraforming often involves modifying a planet's atmosphere, temperature, or biosphere, but in some cases, a complete structural overhaul may be necessary. Planetary shells and artificial crusts offer an extreme but effective way to reshape a world's surface, creating entirely new environments independent of the original planetary conditions. What are planetary shells? A planetary shell is a massive artificial structure built around or within a planet, effectively enclosing or replacing its natural surface. Shell worlds. A new planetary surface is built atop an existing world, enclosing the original surface beneath. This can be done to create a more habitable environment while preserving native conditions below. We often imagine this for mid-sized gas giants like Saturn, whose surface gravity is similar to Earth's. It might also be done on oceanic worlds to place a floating land layer and shallower oceans more compatible with rich marine life over the deeper oceans. Pressure shells. Used on airless or low-pressure worlds, these structures contain a breathable atmosphere, acting like a planetary-scale dome or world house. This can be used to hold air in above the ground people live on, or to wrap a gas giant to form the ground they live on, again as envisioned with Saturn. Thermal and radiation shields. Shells can be used to regulate temperature and protect against solar radiation, ideal for planets lacking a natural magnetosphere. Suspended shells. In cases where a planet has extreme gravity or lacks a solid surface, like a gas giant, floating megastructures could create an artificial ground at an optimal altitude. This could also be used to create multi-level worlds, as we discussed in our episode Matryoshka Shell Worlds. Artificial crusts and planetary restructuring. Beyond the gas of shell worlds, where we use a fraction of the rocky mass a planet normally has to create a shell full of ultra-abundant hydrogen, helium, or dark matter, we have a number of other cases where shells could help. Some worlds may have unstable or inhospitable surfaces, extreme volcanism, toxic soil, or lack of solid land. Artificial crusts could be created by layering materials over these, either through direct deposition of rock and soil, or by using advanced methods like nanotechnology or self-assembly materials. For planets with excessive oceans or liquid surfaces, such as an ice moon with subsurface water, floating crusts could provide artificial land masses, while deep tethers or megastructural supports could anchor structures to a stable depth. In extreme cases, a planet's entire geology might be rebuilt, either through controlled volcanic activity, planetary mining, orbital bombardment, or imported material. For example, a planet with weak gravity and little atmosphere could be given a new crust with denser materials to retain heat and support atmospheric pressure. Terraforming nanotechnology. Terraforming a planet is an immense challenge, often requiring vast industrial-scale operations. What if the process could be done at the molecular level? Terraforming nanotechnology offers a way to reshape planets from the ground up, literally, by using self-replicating programmable nanomachines to modify soil, air, water, and even planetary crusts on an atomic scale. The role of nanotechnology in terraforming. Nanotechnology could dramatically accelerate many of the core processes involved in terraforming. Building terraforming and para-terraforming machinery. Counterintuitively, frequently the best use of tiny little machines is going to be finding, refining, and forging the materials to make larger machines, which can in turn do more specialized roles to assemble even bigger machines. Atmospheric processing. Nanobots could be buoyant and thus could bind or release gases, scrubbing carbon dioxide from Venusian air or breaking down frozen carbon dioxide on Mars to release breathable oxygen. Soil engineering. Microscopic machines could reassemble minerals and toxins at a molecular level, detoxifying alien soils, enriching them with nutrients, or even reconstructing entire land masses. They could do this even faster and more efficiently than a tailored microorganism, and also not need the planet to be livable yet, as a microorganism probably would need, at least to some degree. Biosphere integration. Nanobots could alter plant and microbial DNA to rapidly adapt Earth life to alien conditions, allowing bioforming efforts to proceed more efficiently, or even potentially build life forms from digital templates, or build the equipment needed to gestate larger organisms. This allows it to be deployed far from Earth and humans, such as in a vanguard role terraforming planets in advance of human settlers arriving. Recent advancements in nanomaterials, self-replicating systems, and AI-driven molecular assembly suggest that a nanotech-based approach could one day supplement or even replace heavy industrial terraforming. However, key limitations remain, especially concerning energy and heat dissipation. The heat barrier and limits on nanobots' speed. One of the biggest constraints on nanotechnology is heat generation. Every machine, no matter how small, generates waste heat as it operates. On an industrial scale, even an ultra-efficient swarm of nanobots would quickly overheat unless there was an effective way to dissipate the excess energy. They also had to have some way to receive energy too. This presents a fundamental speed limit to nanobot-based terraforming. The more actively they restructure a planet's atmosphere or geology, the more heat they generate, potentially leading to thermal buildup that could stall or even reverse progress. This means nanotechnology cannot simply be dropped on a planet and turn it into a paradise a few days later. Even a few decades would be optimistic. That's still very handy, and ultimately, while nanotechnology is a tool, not a magic solution, if developed correctly it could make terraforming faster, safer, and more adaptable than ever before. See our nanotechnology episode for more discussion. Also, always keep in mind that nanotech can be used to build bigger devices, which may outperform it in various terraforming roles, so you might use nanotech just to build all the other terraforming devices we've discussed. Tidal and seismic stabilization. A planet's tides and seismic activity are largely shaped by gravitational interactions with nearby celestial bodies. Moons, gas giants, and even the pull of a star Indeed, we can have planet-sized moons around gas giants we want to terraform who receive powerful tidal forces. These forces shape planetary geology, ocean currents, and even atmospheric dynamics, all of which can significantly impact the habitability of a world. Terraforming efforts may require stabilizing or adjusting these forces to create more predictable and livable environments. Lunar adjustments and orbital engineering. One of the most direct ways to stabilize tides and mitigate seismic activity is by adjusting a planet's moons or adding artificial satellites to provide the right level of tidal influence. The orbital position of a moon determines its tidal impact. Over time, moons tend to drift outward due to gravitational interactions. Terraformers might use orbital tethers, gravity tractors, or controlled mass shifts, such as asteroid bombardment or mining operations, to fine-tune a moon's position, or orbital eccentricity, ensuring stable tidal effects over long periods. This technique could also be used to move moons into resonant orbits, where multiple satellites stabilize each other's position and reduce chaotic gravitational effects. Seismic stabilization and tectonic engineering. While tides affect ocean dynamics, seismic activity governs the stability of continents, volcanoes, and geological processes. Excessive tectonic activity can create uninhabitable conditions, but some level of movement is necessary for long-term planetary habitability. Dampening excessive seismic activity. Planets with extreme tectonic movements, such as those with frequent megaquakes or rampant volcanism, may require structural reinforcement at fault lines. This could involve draining magma chambers, stabilizing unstable regions through subterranean supports, or even using seismic dampening structures, massive underground counterweights that reduce stress buildup. Encouraging plate activity. Some planets, such as Mars, appear to have stagnant tectonics, meaning that they lack active plate movement. This can lead to thin, static atmospheres and limited volcanic outgassing, which is essential for replacing a world's atmosphere over time. In such cases, controlled artificial mantle heating or strategic impact events could be used to restart limited tectonic motion, ensuring a long-term recycling of planetary gases. Gas giants and moons settling. Many potential habitable moons orbit gas giants, where they experience extreme tidal heating due to their parent planet's gravity. This is especially true for worlds like Io, which is constantly stretched and compressed by Jupiter's gravitational pull, leading to intense volcanic activity. Terraforming efforts in gas giant systems might involve settling large moons in stable orbits. Many exomoon orbits may be highly elliptical, leading to extreme tidal heating and instability. Terraformers could use orbital adjustments to circularize these paths, reducing violent tidal flexing and creating more stable conditions. Resonance tuning. Several moons in the solar system, such as Europa, Ganymede, and Io, are locked in a gravitational resonance. Adjusting orbits to fine-tune these interactions could optimize heating for habitability, boosting warmth for ice-covered worlds while reducing extreme volcanism on others. Shielding moons from radiation. Gas giants often generate intense magnetic fields that expose moons to high levels of radiation. Terraforming efforts could involve artificial magnetic deflectors, planetary shielding, or moving a moon slightly farther out to minimize exposure. I should also note, as we discussed in our episodes on Jupiter, like colonizing Io, that you can use techniques to drain the radiation out from planetary radiation belts like Jupiter's or our own Van Allen belt, mostly by the same means we use for shielding planets with artificial magnetospheres or Lagrangian magnetic deflectors. Balancing stability and change. Tidal and seismic forces shape the long-term evolution of a planet's climate, oceans, and geology. While some worlds may require increased stability to reduce catastrophic seismic and tidal activity, others may need a controlled boost to encourage essential planetary processes. Through a combination of orbital engineering, tectonic manipulation, and lunar adjustments, terraformers may sculpt planetary environments to achieve the perfect balance of habitability and long-term sustainability. From theory to practice, adapting terraforming to specific worlds. Terraforming is not a one-size-fits-all endeavor. Each world presents its own unique set of challenges, shaped by its orbit, gravity, atmosphere, or lack thereof, geology, and even its relationship with a nearby star. While the previous section explored general terraforming techniques, this next phase will focus on applying those methods to specific planetary conditions. For actual examples of real worlds, See our Outward Bound series episodes like Springtime on Mars, Winter on Venus, Summer on Jupiter, Colonizing Titan, Mercury, Pluto, Neptune, Ceres, the Asteroid Belt, and many, many more. Some planets may be baked under relentless solar radiation, requiring cooling techniques, while others may be frozen in perpetual ice, demanding warmth and atmosphere thickening. Some worlds will struggle with runaway greenhouse effects, others with toxic or corrosive atmospheres, and still more with extreme geological instability or erratic day-night cycles. Terraformers will have to work within the natural constraints of each world, determining whether a full transformation is possible, or if a hybrid approach combining terraforming, para-terraforming, and bioforming is the best solution. In this next section, we will examine the unique environmental challenges posed by different planets and moons, and explore how terraforming strategies must be tailored to each situation. From planets that have no air at all to those with crushing atmospheres, from frozen wastelands to scorching infernos, we will explore how humanity might one day turn the cosmos into a collection of thriving, livable worlds. Extreme radiation levels. Radiation is one of the most formidable obstacles to colonization and terraforming, and it will be a problem all too familiar to those who have traveled there on a spaceship. While Earth's thick atmosphere and powerful magnetosphere shield us from harmful cosmic and solar radiation, many worlds lack such defenses, exposing their surfaces to deadly levels of ionizing radiation. This includes Mars, which has no global magnetic field and only a thin atmosphere, as well as moons like Europa, Io, and Ganymede, which are bombarded by intense radiation from Jupiter's magnetosphere. Even planets far from their stars are not immune, as high-energy cosmic rays permeate the entire galaxy, threatening any unshielded biosphere. Solutions for radiation protection. Terraforming a high-radiation world permits both passive and active shielding strategies. 1. Atmospheric thickening and composition adjustments. A denser atmosphere absorbs and scatters radiation, while gases like nitrogen and oxygen provide some shielding. Additionally, elements like water vapor and ozone can help block harmful ultraviolet radiation. However, building up an atmosphere thick enough to stop cosmic rays is an immense challenge. Magnetosphere Generation. A planetary magnetic field can help deflect charged particles from solar wind and cosmic radiation. As discussed in our section on magnetosphere generation, placing giant superconducting loops or Lagrange point magnetic deflectors around a planet could provide an artificial magnetosphere, reducing surface radiation exposure. 3. Subsurface or dome-based habitats. Early settlers on high-radiation worlds may need to live underground or within shielded domes, using meters-thick layers of rock, regolith, or water for protection. Even if full terraforming is achieved, some areas, like regions near Jupiter, may always require shielded environments. Indeed, almost any effort to colonize the galactic core or new star clusters may require this approach. 4. Biological adaptation. Life may need to be genetically modified to withstand higher radiation. Certain Earth organisms like the bacterium Deinococcus radiodurans can survive extreme doses of radiation, hinting at the potential for bioengineered plants and animals capable of thriving under alien skies. 5. Orbital shades and radiation screens. For worlds bathed in excessive stellar radiation, megamirrors and solar shades can act as partial radiation shields, blocking the most harmful wavelengths while still allowing enough light for warmth and photosynthesis. 6. Terraforming hybrid strategies. Some planets may require a mix of methods. Mars, for example, might benefit from a partial atmosphere thickening, a magnetic deflector at L1, and bioforming efforts to create radiation-resistant crops and organisms. Meanwhile, a high-radiation exoplanet could become a hybrid settlement, where the surface is left to automated machines while human colonies thrive beneath domes or underground, or utilize advanced medicine or genetic engineering to help resist radiation. Ultimately, dealing with extreme radiation levels is a multi-layered challenge, requiring a combination of environmental modification, engineering solutions, and biological adaptation. Terraforming such worlds is possible, but it will demand far more than simply warming the planet and adding air. It will require rewriting the very conditions of habitability. Frequent asteroids and meteor impacts. Some planets and moons exist in danger zones, regions where asteroid and meteor impacts are a frequent and devastating threat. Whether it's Mars, which is constantly bombarded due to its proximity to the asteroid belt, or moons of gas giants, which are pelted by debris trapped in their gravitational wells, many worlds are simply too unsafe for large-scale settlement without mitigation. Even Earth has experienced catastrophic impacts, such as the asteroid that wiped out the dinosaurs. For a planet in an impact-heavy region, terraforming isn't just about making the air breathable or the climate stable, it's about ensuring long-term safety from celestial bombardment. This situation may be far worse in many solar systems where recent events or conditions might allow for thousands of times more impact events than we tend to get nowadays. Indeed, they could result from someone messing up with the delivery of asteroids and comets to a planet, causing long periods of bombardment, or be a hostile action by enemies. For a deep dive on defending worlds from deep impacts, see our asteroid defense and planetary defense episodes. But for a quick review of the options. Strategies for impact reduction. 1. Orbital deflection systems. Terraforming a world vulnerable to asteroid impacts requires early warning and deflection systems. This could involve kinetic impactors to nudge dangerous objects off course, laser ablation to vaporize part of an asteroid's surface, altering its trajectory, gravitational attractors, using spacecraft to subtly change an asteroid's path over time. 2. Clearing the local space environment. If a planet or moon is constantly bombarded, it may be necessary to remove or relocate debris from its orbit. Tugging asteroids into safe orbits could turn a planetary hazard into a resource for mining. Mass driver installations on moons or asteroids could eject debris into interstellar space. Gravity-assisted cleanup operations might leverage the planet's moons or nearby gas giants to clear out unstable debris fields. 3. Planetary shields and impact mitigation. In extreme cases, physical barriers or energy-based shields could be used. Large orbital dust rings or artificial debris clouds could act as impact absorbers, breaking up smaller meteors before they reach the surface. Megastructures like orbital mirrors or space habitats could double as asteroid deflection platforms. Rapidly inflating barriers could be deployed too, along with other physical shielding options we looked at in the Orbital Defense Platforms episode. Force fields or plasma shields are more speculative but could eventually provide active defenses against incoming objects. 4. Surface reinforcement and underground settlements. For worlds where impacts cannot be fully prevented, settlements must be designed to endure them. Underground cities would be the safest option, ensuring protection from even large-scale impacts. Hardened surface structures such as shock-absorbing domes or thick regolith bunkers could help protect colonists. Flexible infrastructure such as modular buildings that can be rapidly relocated or repaired could allow for resilience in the face of frequent smaller impacts. Terraforming a world plagued by frequent impacts is not just a matter of climate and air, it's about securing a stable future. Without impact mitigation, a terraformed planet could face devastating setbacks, losing its atmosphere or biosphere to sudden cataclysmic collisions. But with the right defenses in place, even the most chaotic, asteroid-ridden system can be made into a safe and thriving home for humanity. High-gravity worlds. Terraforming a high-gravity world presents a unique set of challenges. Such planets may be rich in resources, but their intense gravity makes colonization difficult. Even a world just twice Earth's mass would have significantly stronger gravity, affecting human physiology, infrastructure, transportation, and even the local environment. If a planet's gravity were too high, even simple activities like walking or lifting objects could become overwhelming. And extreme gravity could collapse traditional buildings, restrict biological movement, and intensify erosion and atmospheric pressure. In high-gravity worlds, the planets that crush you, we explored several strategies for making such planets more habitable. Structural and technological adaptations. Colonists on high-gravity planets would likely require powered exoskeletons or enhanced muscle augmentation to function effectively. Buildings and vehicles would need to be designed for extra load-bearing capacity, using stronger materials or low center of gravity designs to prevent collapse under intense forces. 2. Orbital rings and reduced gravity belts. A rotating ring system around the planet could provide centrifugal assistance, reducing effective gravity for those living within the habitat. This could also be a vacuum train on a track on the surface at the equator or otherwise encircling the planet. While impractical for entire planetary populations, such megastructures could provide essential relief hubs for work, trade, and medical care. This might result in a highly urbanized equator band. 3. Gravity reduction through mass removal. While extreme, removing planetary mass by extracting heavy elements or launching material into orbit could gradually decrease a planet's surface gravity. This process, though slow, could be integrated into planetary mining operations, as discussed in Harvesting Planets. 4. Terraforming and ecological adjustments. Inhabitants would need to engineer plants and animals adapted to high gravity. Trees might develop thicker trunks, and creatures might become shorter, stockier, or even use buoyant adaptations to counteract gravity's pull. If the planet has a dense atmosphere, flying organisms might still exist, using lift from thick air or hydrogen sacs to float. 5. Seafaring and floating habitats. Since water mitigates some of the effects of gravity on biology, ocean-based civilizations that have bioformed themselves could be aquatic, and might thrive on high-gravity worlds, dwelling in massive floating cities or undersea habitats. High-gravity worlds will test the limits of human adaptability, but given the right tools, technology, and engineering, even these crushing environments could become thriving homes. Highly eccentric orbits. Terraforming a planet with a highly eccentric orbit, one that swings between extreme distances from its star, poses severe challenges. These worlds experience dramatic seasonal variations, not from axial tilt, but from distance to the sun changing. Temperatures can shift from scorching heat near perihelion, closest approach to the star, to deep freezing at aphelion, farthest point. Depending on the planet's atmosphere and rotation, entire ecosystems could be wiped out with each orbit due to massive temperature swings, atmospheric collapse, or severe weather patterns. In Earth's case, our aphelion is only a bit over 3% higher than our perihelion, and by the inverse square drop-off of sunlight with distance, the sunlight is only 7% higher when we're closest compared to furthest. Earth has a very low eccentricity though, and Mars, for instance, has a 45% rise at perihelion compared to aphelion. Generally speaking, tidal forces will slowly decrease a body's eccentricity of orbit, but this occurs far more quickly with moons than planets, as it's mostly a function of distance from the primary. There are strategies for changing or handling high eccentricity, but it's also worth noting that it may be handy for tidally locked planets as a way of introducing some hybrid equivalent to day length or seasonal variation. Strategies for stabilization and adaptation. 1. Orbital adjustments. In some cases, modifying the planet's orbit could be the best long-term solution. Asteroid bombardment, gravitational assists from carefully positioned moons, or tugging the planet with massive solar sails or magnetic forces could gradually circularize the orbit. However, this is a slow and energy-intensive process that might take thousands or millions of years. Atmospheric and geological adaptations. A thick atmosphere with high heat retention could help buffer extreme temperature swings. Planets with deep oceans or subsurface reservoirs might store heat and moderate the climate. Alternatively, planetary-scale geothermal engineering could help regulate temperature, using underground heat reservoirs to maintain stable environments. 3. Adaptive colonization strategies. Rather than terraforming the entire world, civilizations might build mobile cities that migrate between hospitable zones as seasons shift, or use subsurface habitats insulated against temperature swings. Massive domes, ward houses, or orbital mirrors could also stabilize local conditions. You can alter the level of lighting or shading throughout the course of the orbit, and also which parts of the planet are getting lighting or shading, as it need not be uniform with orbital mirrors and shades. 4. Artificial magnetospheres and shades. To prevent atmospheric loss and radiation damage, an artificial magnetosphere at the L1 Lagrange point, as proposed for Mars, could protect the planet during close stellar approaches. You would likely have far more flare and solar wind issue at perihelion. Similarly, orbital shades or solar reflectors could regulate incoming light, reducing extreme heating near perihelion and preserving surface conditions. 5. Biological adaptation and ecological engineering. Lifeforms designed for rapid adaptation could be introduced, with species capable of entering hibernation or cryptobiosis during extreme seasons. Eccentric planets around bigger stars might have orbital periods of entire decades, while worlds around dimmer red dwarfs might merely take weeks or even days to orbit. Genetic engineering might allow human colonists to endure the planetary cycle, either through cybernetic enhancement or modifications that allow metabolic shifts between active and dormant states. you would likely need to entirely modify your planetary ecology to any extreme year-length variation of duration or seasonal intensity. Terraforming a world with an eccentric orbit may require a hybrid approach, blending orbital engineering, planetary modifications, and biological adaptation. While stabilizing such a world is a massive undertaking, it could create a unique planetary environment, one where vast seasonal migrations, underground refuges, and engineered ecosystems evolve to thrive in the extremes. You might opt to inhabit underground or subterranean environments and artificially light them for temporal stability. Hostile native life. Terraforming efforts may not always take place on barren, lifeless worlds. Some planets may already host ecosystems, and not all of their inhabitants will be welcoming. Hostile native life could range from dangerous microbial pathogens to large, aggressive megafauna, or even intelligent beings with their own territorial claims. By default, I assume we would not seek to terraform any planet already containing complex life, in favor of preserving it as rather valuable. There's trillions of planets in the galaxy, and I'd be surprised if even a small fraction held anything more complex than microbial life. Indeed, even that might turn out to be rare. However, native life doesn't have to be classically alien. You might have been sending out automated terraforming ships in advance of any colonists who were planting basic ecologies on planets, meaning when some ship or settlement wave arrives there at 2 to 3% of light speed at the galaxy's edge, 100,000 light years away, there might already be a very established ecology that's run wild and isn't very terrestrial in a modern context. Earth was pretty alien a few billion years ago when life emerged, and we would be as likely as not to be producing something that looks more like that than now, with an automated system just aiming to get soil and ecology running somewhere. Either way, one of the most immediate threats probably comes from alien microorganisms, as the Martian invaders found in War of the Worlds. Native bacteria or viruses could pose a serious risk to human settlers, even if they are biochemically distinct from Earth life. Moreover, while humans can wear spacesuits to protect us from those microbes, any flora or fauna we are transplanting there presumably is not wearing spacesuits, and the native bugs will slowly leak into our protected domes too. While cross-infection between entirely different biologies might be unlikely unless they were terrestrial in origins, alien microbes could still disrupt terraforming efforts by breaking down essential infrastructure, consuming resources, or outcompeting introduced Earth organisms. Medical nanobots might be your best approach to helping humans and other organisms handle the bugs. Larger hostile life forms, whether territorial predators, toxic plants, or hive-minded swarm creatures, could present direct dangers to colonists and equipment. And while we might imagine big dinosaurs and other animals that would be no threat to a technological civilization in spite of their size, the native ecology might be techno-organic, with creatures sporting diamond-hard skin and teeth, especially if these were worlds previously hosting technological life, including planets we'd sent automated terraformers to, which such creatures might be mutated descendants of. Defensive measures might include fortified settlements, automated defenses, or even biological countermeasures like engineered predators or repellents. In some cases, bioforming, modifying human settlers rather than the planets, might allow coexistence rather than conflict. For planets with intelligent native life, the ethical dilemmas become even greater. If an alien civilization exists, the question shifts from how to terraform a planet to whether it should be done at all. Any attempt to reshape a world must consider the rights and survival of its inhabitants. This issue was explored in our Ethics of Terraforming episode, and in cases where coexistence is impossible, the best course of action may be to look elsewhere. The galaxy is huge, and even your typical solar system will have millions of minor planets and asteroids you could settle instead of that planet. Ultimately, hostile native life adds another layer of complexity to terraforming, making it not just a question of engineering and science, but of survival, ethics, and diplomacy. Intense volcanism. Terraforming a planet with extreme volcanic activity presents some fiery problems. While volcanism can provide valuable resources such as heat, minerals, and atmospheric gases, it can also pose a significant threat to both infrastructure and habitability. Frequent eruptions, lava flows, and seismic activity can make settlement difficult, while heavy outgassing can create toxic or unstable atmospheres. One of the primary issues is atmospheric instability. Highly volcanic worlds may have excessive levels of carbon dioxide, sulfur dioxide, or other hazardous gases, leading to a runaway greenhouse effect or acid rain. Large-scale climate control measures such as orbital shades, atmospheric processing plants, or controlled sequestration of greenhouse gases may be necessary to stabilize conditions. Another major concern is tectonic activity. Constant earthquakes and eruptions can disrupt construction infrastructure, making traditional surface cities difficult to maintain. In such cases, floating habitats, underground bunkers, or mobile settlements designed to adapt to shifting terrain might be more viable than static colonies. However, volcanic activity can also be a powerful asset for terraforming. Volcanoes release heat, water vapor, and essential gases, potentially jump-starting atmospheric thickening or hydrospheric formation. Controlled volcanic outgassing could even be harnessed to terraform planets with thin atmospheres, using deliberate geological engineering to release trapped gases. This could be achieved through nuclear detonations in magma chambers or drilling operations that encourage controlled eruptions. Additionally, volcanic energy provides a nearly limitless source of geothermal power, reducing reliance on external energy sources. Advanced civilizations could also redirect lava flows using containment structures, creating fertile volcanic soil for early colonization efforts. In extreme cases, if a planet's volcanism is too severe for direct settlement, it may be more practical to terraform only select regions, using planetary scale engineering to create stable zones while leaving active regions untouched. Alternatively, orbital habitats could serve as the primary living space, while surface operations extract resources and manage terraforming processes remotely. Ultimately, volcanic worlds may be dangerous, but with the right technology and planning, they could also be some of the most energy-rich and resource-abundant terraforming candidates available. Long or erratic day-night cycles. Terraforming a world with an extreme or unstable day-night cycle presents multiple challenges, from temperature swings and weather instability to disruptions in biological rhythms. Planets with slow rotation, tidal locking, or erratic axial tilt, such as Uranus, which is tilted nearly 98 degrees, experience dramatic variations in sunlight, making them difficult for both habitation and ecosystem development. Stabilizing a planet's rotation. In extreme cases, altering a planet's rotation may be necessary. One proposed method involves electromagnetic manipulation, using powerful electromagnetic tethers or planetary-scale flywheels to gradually accelerate or decelerate rotation. Back in the day, our default way of getting power was to spin a metal disc through a horseshoe magnet, and this would work as a megastructure too, letting you slow a planet's rotation for a longer day length while generating power, or adding rotational speed in reverse by taking solar energy and translating it into spin. This could be done by placing large satellites in orbit using the planet's own magnetic field to exert torque over thousands or millions of years. Another option we've mentioned in other sections are controlled asteroid or comet impacts, using precision-guided asteroid strikes to subtly alter angular momentum. While this approach carries risks, it has been theorized as a method for spinning up slow-rotating planets or even breaking high-spin worlds for more manageable day lengths. Essentially, you're sending these in the same as you would for normal cometary bombardment to build up an ocean, but timing them so they hit on the side and either add or subtract angular momentum, rather than evenly or randomly crashing them onto a planet. And beyond a small bit more effort to be timed and precise, this does not use any more energy or effort to alter day length than just dropping them normally would. A carefully managed long-term impact strategy could make a planet's rotation more Earth-like without requiring excessive external energy inputs. Managing extreme day-night cycles. On tidally locked planets, one hemisphere is permanently baked under the sun while the other remains frozen in darkness. Gigantic orbital mirrors or rotating solar shades positioned at Lagrange points could redirect light and create an artificial day-night cycle. Similarly, atmospheric heat redistribution using planetary-scale weather control systems could prevent the day side from overheating and the night side from freezing. Instead of having a dark side, an eternal day side, and twilight band running around the planet through the poles, you have some mirrors on the day side rotating from the sun to cause a day-night period and bouncing that light over to the other side to light it. There are several ways to do this, and the planet's Lagrange points with its star are great places for your mirror arrays, as it's a cloud of remote-controlled mirrors orbiting the planet that can simply rotate as they orbit, turning sideways to let light through and then perpendicular to block it. Though this isn't a good way to achieve total coverage and risks Kessler syndrome. Not every planet has stable Lagrange points either. Many moons do not, and we deep dive some of the methods for handling daylight without stable Lagrange points in our episode Can We Terraform the Moon? As you might guess, the answer is yes. Now, for planets with highly variable day lengths, such as those with erratic axial tilt, artificial lighting and climate stabilization techniques would be necessary. On planets like Uranus, which experience extreme seasonal shifts due to its nearly horizontal axis, terraforming efforts would need to account for 42-year-long summers and winters in each hemisphere. One option is placing a massive ring of mirrors around the planet's equator to redistribute light evenly. Another is terraforming only specific latitudes where conditions remain more stable. Axial tilt adjustments. Altering a planet's axial tilt could significantly improve habitability. While this is an enormous engineering effort, it might be possible using gravitational interactions with moons or mass redistribution on the planet itself, such as constructing massive artificial ice caps or moving large amounts of material to the poles or equator to gradually shift its tilt. Another speculative approach would be to construct artificial moons or reposition existing ones to exert long-term gravitational influence, slowly adjusting a planet's axial tilt over millennia. Bombardment works, so does a space tower with a huge mirror on it coming up from the surface that you can focus a powerful energy beam on, or a magnetic sail you could focus an ion beam on, probably hydrogen solar wind from the sun. You can have these rise over the atmosphere and be like paddles on a water wheel, and use your light or particle beam to slow, speed up, or tilt a planet or tweak its orbit. As usual, it's handy in newly colonized systems where you may have constructed such a beaming array to permit follow-up waves of colonists to reach your new system faster and cheaper by being able to slow them down without onboard fuel. When not doing that task, it can be doing other jobs like this, or boiling the atmosphere of super-Earths or gas giants for that matter. You could use it to fix a tipped-over planet like Uranus and remove its super-thick atmosphere and make it habitable. Adaptive habitats and hybrid solutions. Rather than modifying the entire planet, another solution is adapting human settlements to fit the conditions. On slow-rotating worlds, cities could be built on massive mobile platforms that migrate across the surface, keeping pace with the planetary twilight zone. Underground or sealed dome habitats with controlled lighting could also provide an Earth-like day-night cycle, even if the planet outside experiences wildly fluctuating light levels. For worlds with erratic day lengths, genetic modifications to crops and human circadian rhythms might be necessary to adjust to variable daylight cycles. This could involve bioengineering organisms to function under extreme photoperiods or using advanced cybernetic sleep cycle management for human settlers. Terraforming within constraints. Ultimately, while extreme day-night cycles present a significant obstacle, there are multiple ways to adapt or modify planetary conditions to make such worlds habitable. Whether through planetary-scale engineering, orbital infrastructure, or adaptive biology, civilizations looking to terraform such worlds would have many tools at their disposal. The key is balancing technological intervention with natural processes to create a stable, livable environment over time. Low gravity. Planets and moons with low gravity present numerous issues for long-term habitation, including muscle atrophy, bone loss, and difficulty retaining atmosphere. While bioforming and artificial habitats can mitigate some of these issues, various terraforming techniques could help create a more Earth-like environment. The most common and conventional solution people suggest is simply adding mass from asteroids or moons. This is an incredibly resource-intensive approach, as we discussed earlier. By directing large volumes of rock, ice, or metal-rich asteroids to collide with the planet over time, its total gravitational pull can be increased incrementally. However, this method is extraordinarily slow and requires vast amounts of material. It also generates huge amounts of heat which must be radiated off. But it remains a viable long-term strategy, particularly for moons or dwarf planets near the mass threshold for retaining an atmosphere. To put the scale into perspective, even if we add the entire asteroid belt to Mars, its mass would only increase by about 0.5%, resulting in an even smaller increase in surface gravity. A far more mass-efficient approach would be to construct a massive shell around the original planet, or even several shells, and fill them with gas from a neighboring gas giant. By default, this would create a world with Earth-like gravity but the size of Saturn, providing 100 times the living area of Earth while using less rocky material than Mars itself, Such a planet would require extensive north-south mountain ranges or atmospheric barriers to mitigate the extreme storms caused by its high rotational speed, necessary for maintaining a 24-hour day, but that may actually be a preferable option in the long run. And mountains packed with aerogel can be made pretty tall. One more local para-terraforming solution is the Bullhab, a vast concave spinning habitat embedded into the surface of a low-gravity world. The spin of the structure generates artificial gravity via centrifugal force, allowing settlers to live in a more Earth-like environment while still benefiting from the natural resources of the planet or moon. This concept, discussed in our episode The Domes of Mars, offers a scalable and practical approach to addressing low gravity without modifying the entire planet. I should note that these will usually not be a shallow bowl, but a lot steeper in most cases, more like a vase or urn. The weaker the surface gravity, the steeper the bowl. I will also note that if surface gravity is less than 1%, which is the case for virtually every asteroid and the supermajority of moons, you can just embed a regular cylindrical rotating habitat, and even if you had it lying on the surface, the shift in gravity as you spun up and down would be pretty minimal and likely not bother those inside. You might even use it to help stir the water and air around. Another extreme approach we've already mentioned is placing an artificial black hole at the planet's core. A sufficiently small, stable black hole could generate additional gravity, mimicking the effect of a denser planetary core. Surprisingly, such a system would not immediately consume the planet, as matter falling into the black hole would form a dense, superheated plasma barrier that effectively regulates further intake. We explored this in depth in our episode Moon Megacities, highlighting how controlled singularities could alter planetary conditions without catastrophic consequences. Needless to say, artificial gravity generators might be even better if we have developed such technology, though they may also need power to run them. See our Gravity Tech episode for discussion of how power maintenance gravity generation would alter the equation. Low light levels. Planets with dim or distant stars, thick atmospheres, tidal locking, ultra-slow days, high eccentricity orbits, or extreme axial tilts may struggle to receive sufficient sunlight for warmth and photosynthesis. This issue is particularly severe for the dark side of tidally locked planets or worlds like Uranus, which spend decades with one hemisphere in shadow. A practical solution is the use of orbital mirrors or Lagrange point reflectors to redirect sunlight. Immense parabolic mirror arrays positioned at a planet's L2 point, directly behind it relative to its star, could illuminate dark hemispheres, providing consistent daylight. Mirrors can be rotated as individual pieces of a wider array to reflect light elsewhere to allow nighttime, and potentially power orbital industries. Similarly, L1 point sunshades could regulate light levels on a world that receives too much radiation. Mirrors and shades can be built to reflect or block certain wavelengths too, letting you tweak the spectrum you receive around redder stars or remove harmful wavelengths. These mirrors would not only support plant life but also help regulate climate, making even the most light-starved planets more habitable. You can also surround a planet with billions of mirror-shade satellites capable of swiveling on command or adjusting based on the time of day. This not only provides controlled lighting, but also serves as a defensive shell against Nikola-Dyson beams, Death Stars, and relativistic kill missiles. However, such a dense satellite network poses a constant risk of Kessler syndrome, where cascading collisions create an ever-growing field of orbital debris. Hence the use of statites, static satellites which orbit at very low speed or not at all, may be a better option, as their collisions would not cause cascades. See our episode on statites and ligites for details. No air. A planet or moon lacking atmosphere presents an obvious challenge for terraforming. Fortunately, oxygen is one of the most abundant elements in the universe and is plentiful in rock and ice. On airless worlds, one approach is baking oxygen out of surface minerals, a process similar to industrial metal refining. By heating native regolith-rich in oxides, we can extract and release oxygen gas, though this alone is not enough. A breathable atmosphere also requires nitrogen or other buffer gases. This can be a byproduct of metal or fuel production, or you can nuke a planet till it glows in the dark, or blast it with a powerful stellaser or other sun-powered beaming device. Both of those options are a lot saner than they probably sound like. Another method is importing volatiles from icy comets or moons, delivering nitrogen, carbon dioxide, and water vapor to help thicken the atmosphere. This is a slow but steady process that could provide the necessary components for a stable air supply. However, retaining atmosphere long-term is another issue. Low-gravity worlds will struggle to hold onto air over geological timescales even with a fully established atmosphere. Shell worlds or world houses, giant transparent domes, or artificial planetary crusts offer an alternative by physically enclosing the atmosphere. Even for planets with higher gravity, a strong magnetosphere is necessary to protect the air from solar wind stripping. And that brings us to our next challenge, creating an artificial magnetosphere. No magnetosphere. A planet with a natural magnetosphere is vulnerable to solar wind stripping, which gradually erodes its atmosphere as seen on Mars, and we discussed the option for this in depth in our episode Making a Magnetosphere for Mars. Without protection, even a carefully built atmosphere would be lost over time. The best solution is to generate an artificial magnetosphere, which we discussed already in that episode and earlier today in the Magnetosphere Generation section. As a quick recap, this could involve placing large electromagnetic shields at the planet's L1 Lagrange point to deflect solar wind, or even creating a planetary-scale magnetic field by running massive electrical currents through underground superconducting loops. For smaller bodies, a magnetically charged shell world or domed habitats could offer localized protection. Without this protection, any terraforming effort will be an uphill battle, making magnetosphere engineering a critical first step before large-scale atmospheric transformation. It's important to understand that all stars emit solar wind, and many are far more intense than our own sun. More volatile stars, such as young red dwarfs or active G-type stars, produce frequent flares and coronal mass ejections, which are disproportionately effective at stripping atmospheres away. The magnetosphere also results in powerful radiation belts filled with high-energy ionized particles, which can wreak havoc on orbital habitats and infrastructure. Over time, these radiation zones can degrade satellites, increase astronaut exposure, and make stable orbital industry or colonization difficult. Because of this, artificial magnetic shielding may become standard for all inhabited worlds, not just those lacking natural protection. Even Earth itself might one day deploy an L1 magnetic deflector, not for atmospheric retention, but to reduce radiation exposure in orbit and improve long-term spaceflight conditions. No seasons. We often take Earth's seasonal cycle for granted, but this is not the norm for habitable zones. Most stars in the galaxy are low-mass red dwarfs. Many of those will have planets in the habitable zone that are tidally locked, with one side facing perpetual daylight and the other in eternal night. Many others, bigger red dwarfs or orange dwarfs, simply have very reduced habitable zones that wouldn't even go out to Mercury's orbit, and thus we're talking a year of maybe a few months at the most and a season of mere weeks. Even among sun-like stars, many planets will have minimal axial tilt or highly eccentric orbits, leading to extreme seasonal variations or none at all. A world without seasons may seem idyllic. Indeed, it is one of the few reasons to create a megastructure known as a disk world or flat Earth, but it can present challenges. Stable climates can lead to stagnation in ecosystems and limiting biodiversity. Conversely, planets with extreme temperature swings, due to eccentric orbits, may face cycles of rapid freezing and scorching, making habitability difficult. Terraforming solutions include altering axial tilt, which could be done gradually with asteroid impacts or artificial mass redistribution, or something along the lines of the laser or particle beam water wheel megastructure in the long or erratic day-night cycle section, or the solar pinwheel from our episode Colonizing Mercury. Orbital mirrors and shades can also regulate lighting, either introducing an artificial day-night cycle for tidally locked worlds or balancing temperature extremes on eccentric orbit planets. A system of orbital reflectors could mimic seasonal shifts, ensuring climate variation suitable for agriculture and ecosystem stability. By reshaping a planet's environmental conditions, we could create habitable worlds tailored to human needs, and terrestrial flora and fauna, even if their natural cycles differ wildly from Earth's. No water. Water is essential for life as we know it, yet many otherwise promising planets may lack surface water, either because they formed dry or lost over time. Earth's oceans contain about 1.4 billion cubic kilometers of water, about 0.023% of Earth's mass, which, while vast, is still a small fraction of the planet's total mass. Transporting that much water to a dry world would be a monumental challenge, but we have abundant sources to draw from. The Kuiper Belt, a vast region of icy bodies beyond Neptune, holds hundreds of times more water than the asteroid belt, as most Kuiper Belt objects, KBOs, are composed primarily of water ice, and what isn't water tends to be useful volatiles like nitrogen-rich ammonia. Even further out, the Oort cloud might contain thousands of times as much water as the Kuiper belt, making it the largest reservoir of potential water in the solar system. By comparison, a comet like Halley's Comet, which has a mass of about 2.2 times 10 to 14 kilograms, contains a tiny fraction of Earth's water. So moving a significant number of comets or Kuiper belt objects would be necessary to hydrate an entire planet, millions of them. For planets closer to home, icy moons such as Europa, Triton, and Ganymede could provide large amounts of water. Redirecting small icy asteroids and comets from these regions might be easier than hauling material from the outer solar system. Another approach is to synthesize water in situ by extracting hydrogen from gas giants such as Jupiter and Saturn. These planets are rich in hydrogen, which, when combined with oxygen extracted from a dry planet's crust, could produce water directly. A similar process could work via solar wind collection, in reverse of the solar wind deflection we've suggested for artificial magnetospheres in other sections, harvesting hydrogen ions streaming from the sun and combining them with planetary oxygen reserves. For more advanced civilizations, star lifting, the process of siphoning material directly from a star, could provide hydrogen in enormous quantities, allowing for large-scale water production. Over long timescales, civilizations could reshape a dry world into a water-rich one through these techniques, making even the driest planets viable candidates for terraforming. In short, while water scarcity presents a significant challenge, the sheer volume of ice and hydrogen available in our solar system and beyond offers numerous pathways to hydrate an arid world. Short or long seasons. Planets with extremely short or long years experience drastic differences in climate stability. A short year, such as those of planets orbiting closer to their stars, can cause rapid seasonal shifts, with extreme temperature swings between summer and winter. Conversely, a long year means that seasons can last for decades or even centuries, leading to prolonged ice ages or scorching heat waves. Axial tilt plays a critical role. A planet with a high tilt may experience more extreme seasons, while a low tilt planet may have mild or even non-existent seasonal changes. If a planet's orbit is highly elliptical, it might have wildly unpredictable seasons, with blistering summers and frozen winters regardless of tilt. For habitability, stabilizing these effects may require artificial climate control, such as orbital mirrors to regulate sunlight, massive planetary-scale heat pumps, or even adjusting a planet's orbit over millennia with gravitational engineering. Without intervention, extreme years and seasons could render a planet's surface hostile to stable civilizations. Needless to say, if the planet's orbit is too hot or cold, seasons or year length can be fixed in part by moving the whole planet to a different orbit, or by employing arrays of solar mirrors or shades. Tidally Locked. A tidally locked planet always shows the same face to its star, creating a world split between eternal daylight and perpetual night. We explored this topic in depth in our episode Colonizing Red Dwarfs and Tidally Locked Planets, and have already touched on it today, so we'll keep this brief. The day side may be scorching hot, while the night side could be frozen, leaving only a thin twilight zone as the most habitable region. Some of these planets may receive so little light that even the day side remains dim, requiring artificial illumination. These worlds are not limited to red dwarfs either. We may find them around white dwarfs and brown dwarfs, where they effectively function as moons, introducing entirely different dynamics. In their early days, some tidally locked planets might have wide twilight zones along their poles, and orbital eccentricity or libration could allow for shifting sunrise and sunset conditions inside these regions. This is another case where orbital mirrors and shades, especially those positioned at Lagrange points, can be invaluable terraforming tools. Despite their immense size, they could be incredibly cost-effective since they only need to be tinfoil thin. Strong atmospheric or ocean circulation might also help distribute heat, expanding habitable zones. Terraforming efforts could involve giant orbital mirrors to warm the night side, atmospheric thickening to enhance heat transfer, or artificial sun reflectors to balance temperatures across the planet. Tidally Wracked. Some planets experience intense tidal forces, causing extreme geological activity. If the world orbits close to a massive body, like a gas giant or a binary star, tidal flexing could generate constant earthquakes, volcanic eruptions, and planetary stress fractures, and even tidal waves of stone or lava. and this is likely very common for moons of gas giants like Jupiter's moon Io. I mentioned brown dwarfs in the last section, and depending on if we count these as stars or planets themselves, they could have planets or moons around them, and in either case, Earth-sized ones. This could create a warm, geologically rich world, which might have abundant life even without any sunlight from that brown dwarf or some possible binary star nearby, but it might also make stable settlements impossible. Terraforming efforts would need to either stabilize the crust through megastructure engineering or build floating mobile habitats to avoid the most unstable regions. See our episode Colonizing Io for more on such tidally racked worlds. Too cold. A planet too far from its star may be locked in an eternal deep freeze, with only subsurface oceans remaining liquid. Once again, orbital or Lagrange point mirrors can help. Even very distant planets can be warmed simply because a mirror is so much thinner than a planet. Thus, even a modest asteroid could let us create a mirror hundreds of times wider than a planet, or an array of them, able to warm something as far from the Sun as Pluto. Though given that it's a low-density ice ball, this might not be a great plan. To warm distant rocky planets, parabolic mirrors at the L2 point, or a halo orbit around it, could focus additional sunlight onto the planet, supplementing internal heating from nuclear decay, controlled geothermal releases, or greenhouse gas seeding. Other solutions previously discussed, such as redirecting comets for water vapor, atmospheric thickening, or Dyson swarms redirecting power towards such a world via energy beaming, could also help increase planetary temperatures. Too hot. Overheating can be caused by excessive sunlight, a thick greenhouse atmosphere, or a runaway climate system. Solutions include sunshades at L1 to reduce incoming radiation, massive orbital reflectors to redirect heat, or altering the atmosphere by reducing greenhouse gases and introducing cooling aerosols. See our episode Winter on Venus for a discussion of the options and the timeline of the process, including options like enormous cooling towers, Lagrangian solar shades, and seas of carbon dioxide. If the heat is due to an overly thick atmosphere, gradual atmospheric stripping using magnetic sails, large-scale chemical reactions, or even terraforming bacteria might be necessary to make the planet livable. Too much air. Speaking of too much air, a planet with excessive atmospheric pressure like Venus could feel more like the bottom of an ocean than an Earth-like world. Breathing could be impossible without specialized adaptations, and high pressures might even create exotic weather patterns like supercritical carbon dioxide oceans or permanent cloud cover. Reducing atmospheric mass could be done through slow gas extraction into space, chemical sequestration, or even building high-altitude habitats where the air pressure is more tolerable, potentially even continent-sized ones, such as we explored in colonizing Venus. Alternatively, engineered life forms might adapt to the conditions, transforming the atmosphere over thousands of years. Too much ocean. Just as a world with too much air might feel like being trapped beneath an ocean, a planet with too much actual ocean could be just as inhospitable. A true water world, covered by kilometers of liquid, might lack the land needed for traditional civilization, industry, or farming. The crushing depths could also prevent plate tectonics, halting critical geological cycles like carbon sequestration and mineral replenishment. Over time, a world like this could stagnate, its oceans turning into a nutrient-starved expanse unable to support complex ecosystems beyond its surface layers, simply because the sunlight on the surface water, abundant though it might be, cannot fuel plants that can't exist without the nutrients buried far below. As we discussed in our Hycean Planets and Ice Worlds episode, as well as the Ocean Habitats episode, these may be the supermajority of planets with atmospheres, or the ability to host one without massive terraforming and para-terraforming efforts. Solutions could include massive floating cities, artificial islands, or even gigantic geoengineering projects to create land by raising portions of the seabed or evaporating excess water. You might even build a shell partially under the water to serve as a new seafloor that is shallower. If the planet has icy poles or frozen depths, harvesting and exporting water, perhaps to Mars or other dry worlds, could provide a long-term method of reshaping the surface. Otherwise, megastructures like orbital shades could cool portions of the ocean to form permanent ice caps, creating stable landmasses to support settlement. Needless to say, if you have functioning wormholes or stargates, draining water from one ocean planet onto a desert planet might be a good way to kill two birds with one stone. Too much solar wind. A planet too close to its star, or orbiting one with a particularly intense solar wind, could face constant radiation storms and atmospheric stripping, making it hazardous for life. Without a strong magnetosphere, the relentless bombardment of charged particles could gradually erode the atmosphere, much like what happened to Mars. On the other hand, if the atmosphere is thick enough, solar wind could create powerful electrical storms, auroras visible even at the equator, and even hazardous electromagnetic effects that could interfere with technology. Terraforming efforts would likely require massive magnetic field generators, either in orbit at Lagrange points or on the surface, to deflect the worst of the solar radiation, and ideally powered by solar radiation. If the planet still has an atmosphere, shielding infrastructure, such as underground habitats or reflective orbital defenses, could protect settlers from radiation exposure. An alternative approach could be terraforming the entire magnetosphere, using vast superconducting loops at the poles to generate a protective field. Now, we've mentioned magnetic deflectors a lot in this episode, but using the context of a planet around a single star and with stable Lagrange points with that star, and that won't work on moons or planets around binary stars or other cases too, without modification. It's handy that a magnet doesn't have to be a bulky thing and that a power collector is probably very thin, and this allows us the option of employing a lagite, a mix of a solar sail and a satellite, or thin megastructure to allow a non-Keplerian orbit, or basically something that can hang out in between two bodies in space where normal orbits wouldn't allow, and without huge amounts of thrust and fuel being required. Indeed, they could be deflecting solar wind or gathering it to harvest and use, and in part as a fuel for an ion drive for station keeping. See our Statites and Lagites episode for more discussion of these very handy devices. Key notion though is that they allow placement of mirrors, shades, deflectors, and shields at places we wouldn't expect, and to keep themselves there, thus can be used to deflect particle radiation from some distant binary partner, or even from some radiation source like a galactic center, an active galactic nucleus or quasar. This isn't limited to solar wind either. This could be a big thin inflated shield designed for stopping ionizing radiation, or enemy weapons. We also need to be mindful that many stars give off far more solar wind than our Sun, and often in catastrophic bursts that make a solar flare, or even a coronal mass ejection, seem like a hiccup. Toxic or corrosive atmosphere or surface. Some planets may have atmospheres or surfaces that are outright hostile to both life and technology. Venus, for instance, while once thought to be a paradise planet, turned out to be a suburb of hell, with a molten surface buried under hundreds of miles of toxic air where it rains acid. Instead of breathable air, the sky might be filled with sulfuric acid, chlorine gas, or even more exotic corrosive elements. Even high-pressure oxygen is quite dangerous. The surface itself might be covered in highly reactive minerals like Venus's lead-melting landscape, or have oceans of ammonia or methane that dissolve most materials. The regolith we hope to make soil from may be worse than a toxic waste dump. Indeed, even oxygen turns into acid at higher pressure, and many worlds might have entirely breathable air, just racked by such fast and terrifying storms you'd be shredded by the sand and grit carried by it. Not just the sky and the surface might be toxic either, the seas may be poisonous. In such environments, even advanced robotics or synthetic materials might degrade quickly, requiring constant maintenance. This need not be too extreme either. We believe Earth's oceanic salinity has been both higher and lower in the past, potentially more than double as salty, and that would be murderous on modern life forms or equipment. Survival on such a world would demand sealed environments, anti-corrosion materials, and extensive filtration systems. If possible, long-term terraforming might involve neutralizing the dangerous chemicals through large-scale chemical reactions, precipitation methods, or even engineering microorganisms that consume and convert hazardous compounds into something more stable. Ammonia and methane aren't anything you want to breathe, but they can be easily turned into the stuff of life, and we may be able to engineer organisms that thrived on them and spit out more hospitable byproducts for us, much as we believe Earth's original atmosphere eventually accumulated oxygen as a waste product of early life that slowly poisoned off those organisms that didn't adapt. See our Primordial Planets episode for discussion. Toxic land, on the other hand, may be easier to manage in the early days compared to more extreme surface challenges like the volcanic activity we discussed earlier or the unstable tectonics we'll cover shortly. It's a strong reminder that planetary domes aren't just for shooting above, you also need protection below. You don't create soil by simply digging into the regolith beneath you. Instead, you place a liner inside a dome and cultivate soil in controlled vats before layering it in. This process may require a variety of techniques to remove toxins or heavy metals. Even those living underground in tunnels will need protective liners, as inhaling the dust from the local regolith could be lethal, just as lunar dust would likely shred human lungs. Of course, underground living presents its own challenges, particularly on a planet with significant seismic activity. Unstable tectonics. A planet with an overly active geological cycle could pose significant threats to long-term settlement. Some worlds might be riddled with earthquakes, experiencing constant seismic activity that makes stable construction difficult. Others could have hyperactive volcanism, with supervolcanoes erupting frequently enough to coat the sky in ash and alter the climate unpredictably. Worse, a planet with runaway mantle plumes might be reshaping its surface so violently that no permanent structures could last for more than a few centuries before being buried or shattered. Terraforming a planet like this would require advanced seismic forecasting, shock-absorbing infrastructure, and possibly even geological engineering to stabilize the mantle and crust. Massive underground support systems, such as deep pressure release tunnels, could help regulate tectonic activity over time. We discussed some extreme geoengineering options in our episode Accessing Earth's Core, as well as colonizing Io for tidally wracked planets or moons. Wrong air composition. Even if a planet has a stable atmosphere, the composition might be completely unsuitable for human respiration. Some worlds might have a high percentage of carbon dioxide, methane, or ammonia, creating a suffocating environment. Others could be rich in oxygen but lack nitrogen or other inert gases, making the air dangerously flammable. Some might even have bizarre mixtures of neon or argon, making them chemically inert but still unbreathable without specialized equipment. This is different from our case of a couple entries back where we discussed toxic or corrosive atmospheres, as in many cases we could live there just fine, maybe even without being inside a pressurized dome made of normal Earth air mix. As before, terraforming a world with the wrong air would require large-scale gas processing, with robotic factories converting the atmosphere into something close to Earth's mix, but could allow major human habitation from the outset. Genetically engineered microbes could also play a role, slowly altering the air composition over millennia. In extreme cases, if changing the atmosphere proves impractical, living in enclosed biodomes or high-altitude habitats with controlled air supplies might be the only viable solution.
Final thoughts. Terraforming is no easy task, and the challenges we explored today show just how difficult it can be to make an alien world into a true second home. Yet with the right technology, ingenuity, and determination, even the most extreme planets may one day be transformed into thriving ecosystems. We have only touched on some of the more challenging cases we might encounter and solutions we might use today. Make sure to check out our many other episodes deep diving these topics, including building planets and altering or making the stars themselves. But as we saw, whether through vast orbital mirrors, engineered atmospheres, or entire continents raised from the depths, humanity has the potential to forge new worlds and reshape the cosmos itself.
The road ahead is long, but every world offers new possibilities, and perhaps, in the end, the only truly uninhabitable planet is the one we never try to change.